Hello. Hello. May I have your attention, please? This is an announcement that the guest has already arrived and we are going to start the session in 5 minutes. Hello. 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 A very good morning to everyone present here. On behalf of the organizers, I take this privilege to warmly welcome all the distinguished guests and delegates to the two-day seminar on Plasma for Space and Aerospace Applications 2022, organized by Institute for Plasma Research, Gandhinagar. As you are all aware, the theme of today's seminar is Plasma for Space and Aerospace Applications, with a focus to provide a common platform for synergistic interaction amongst the space and aerospace professionals across the country. The seminar will have a series of talks on various aspects of plasma applications in space and aerospace sector, and we sincerely hope that the ideas, views, and knowledge shared during the interactions will sow its seeds for a sustained, continuous, and fruitful national collaboration. On this occasion, we are also celebrating 25 years of Facilitation Center for Industrial Plasma Technologies, which is also known as FCIPT. FCIPT was established in 1997 with a vision to promote plasma technologies for various societal and industrial applications. With these notes, let's begin with today's inaugural program. We are extremely honored to have with us Dr. Anil Kakodkar, Chancellor, Homi Bhabha National Institute, Member, Atomic Energy Commission, and former Secretary, Department of Atomic Energy as the chief guest. We also have among us Shri A.S. Kiran Kumar, Vikram Sarabhai Professor, ISRO, and Member of Space Commission, Government of India as the guest of honor. We also have with us Professor P.I. John, founder of FCIPT and former senior professor of IPR as the distinguished guest. May I now invite all the delegates, Dr. Anil Kakodkar, Shri A.S. Kiran Kumar, Professor P.I. John, Dr. Shashank Chaturvedi, Dr. P.K. Atre, and Dr. Suryakant Gupta to kindly come forward to the dais. Light symbolizes victory over darkness and defeat. Light symbolizes victory over darkness and defeat. Anil Kakodkar, Chancellor, Homi Bhabha National Institute. Thank you, sir. May I now request Dr. Suryakant Gupta, convener PSAA, to kindly felicitate Shri A.S. Kiran Kumar, Vikram Sarabhai Professor ISRO and member of Space Commission, Government of India. Thank you, sir. Now I request Dr. Mukesh Ranjan, co-convener PSAA, to felicitate Professor P.I. John, founder of FCIPT and former senior professor of IPR. Now I request Shri Akshay Vaid, co-convener PSAA, to felicitate Dr. Shashank Chaturvedi, Director IPR. Now I request Dr. Alfonso Joseph, Head, Plasma Surface Engineering Division, to kindly felicitate Dr. P.K. Atre, Chairman, PSAA. Now I request Dr. Neerav Jamnapara to kindly felicitate Dr. Suryakant Gupta, convener, PSAA. Thank you, sir. May I now invite our director, Dr. Shashank Chaturvedi, to kindly deliver the welcome address.
Respected Dr. Anil Kakodkar, Dr. Kiran Kumar, Professor John, Dr. Arunachal, Dr. Shanbag, Dr. Ganeshan, Mr. Kranchi Chand, distinguished invitees, participants. It's a pleasure to welcome all of you to this two-day seminar on plasma for space and aerospace applications. As another thing, FCIPT is also commemorating 25 years of its formation. So over the past 25 years, FCIPT scientists and engineers have been performing translational research involving development and deployment of a variety of technologies for societal and industrial applications. IPR's efforts for the indigenous development of advanced technologies, whether they be societal or in the fusion field and others, are even more important today, given the government's thrust towards Atmanirbhar Bharat. Plasma technologies have been playing an increasingly important role in the space and aerospace sectors. IPR has been actively involved in developing technologies relevant to the space sector, including propulsion, development of diagnostics and characterization of plasma clusters, investigating space plasma interactions with solar panels, development of cryopumps, and so on. More recently, we have started efforts over the past 2 or 3 years. We have started efforts to investigate plasma-assisted drag reduction, plasma antennas, numerical modeling of all these phenomena based on high-performance computing, and so on. And you will be hearing something about this in this two-day seminar. There's also, I think, a tour of FCIPT planned, and for people who stay back, tomorrow there's a limited tour of IPR. Now, IPR's potential contributions in many of these areas are based on decades of basic research into the underlying science of plasma. So it's very important to understand that the basic research over, say, 30 years or more than that of IPR is what has led to these things becoming available. Added to this is indigenous technology development and development of facilities in areas like high and low power RF and microwaves, sophisticated power supplies, ultra-high vacuum systems, remote handling and virtual reality systems, high heat flux testing, ion and neutron irradiation, and so on. Again, some of these are things that you'll be hearing talks about today and tomorrow, and maybe seeing some of them during the tour of FCIPT and also a tour of IPR. What I would like to emphasize is because of the limited time available, in 2 days, it wasn't possible to organize too many tours. In FCIPT, you'll see most of the interesting things, but in IPR, there'll be a lot more that will be left over. So we'd like to invite more of you to come back to IPR and see more of the technology that we have to offer. Now, apart from technology and system development, IPR's research activities also contributing to human resource development in India in these fields. A quick survey that we did a few days back, incidentally just about a week back, a quick check on some numbers, showed that at least 10 of IPR's PhD students are currently working in advanced technology industries worldwide, including several in aerospace-related fields in India. I believe some of them also participating in this seminar. Now, looking to the future, IPR has recently worked out a 25-year roadmap covering the development of a sort of kind of three-pronged development. This will involve the development of fusion power machines, tokamaks, fusion technologies, an entire indigenous program for developing all the fusion technologies that are required. That is prong one. The second prong is societal applications of plasmas. And the third is what we call directed basic research. Basic research, which has a particular end visualized right now. Now, these things will involve a lot of technology development, and what we are planning is to do and to organize almost the entire thing in PPP mode. So again, after this, over the next few months, we'll be inviting industries, MSMEs, large industries, everyone, to come and hold brainstorming meetings on trying to identify potential partners. And the PPP mode that has to be worked out, the details of that, the participation of industry has to be worked out in a case-by-case area. For example, just if you look at the societal applications themselves, the applications in fields as varied as space and aerospace, which is what the sort of subject of this seminar, but there are also applications in waste disposal, eco-friendly waste disposal, the applications in industry, increasing the lifetime of industrial tools, the applications to textiles, improving the properties of textiles, eco-friendly processing, and a whole range of things like this. So this is, you can regard this particular symposium as just one of the applications. And we feel that in this entire program, 25-year program, the space and aeronautics applications of plasmas will be one of the verticals. But there'll be many more verticals like this, application in the medical field, healthcare fields, sterilization fields, and so on. So I hope that the topics covered during the seminar will strengthen the linkages between IPR, between the government sector in the space sector in India, and private organizations working in this. Thank you.
Thank you, sir. We have among us Dr. Anil Kakodkar, Chancellor, Homi Bhabha National Institute, Member, Atomic Energy Commission, and former Secretary, Department of Atomic Energy. Dr. Anil Kakodkar is an eminent scientist and an academician who has worked for the development of atomic energy program in India. The focus of his work has been on self-reliant development of nuclear reactor systems. He has played a key role in design and construction of the Dhruva reactor starting from its conceptual stage. He has also been a key contributor to the India's strategic program. With these words, may I now graciously invite Dr. Anil Kakodkar to kindly address the audience.
Dr. Kiran Kumar, Dr. Shashank Chaturvedi, Professor John, Professor Atre, Professor Gupta, distinguished invitees and participants to this two-day program on applications in space and aerospace, plasma applications in space and aerospace. Ladies and gentlemen. Well, first of all, let me express my gratitude to Dr. Chaturvedi for this invitation. I always like to come to all our labs, especially a lab like IPR. And of course, I have come to IPR more often, but I have come to FCIPT only once in past, and that's long time in past. So I'm very grateful that I have this chance to be here and also later see the facilities and activities here. This particular meeting is, of course, focused on space and aerospace applications. And I don't want to carry the coal to Newcastle when Dr. Kiran Kumar is here. Uh, but more broadly, uh, I think applications of plasma, of course, IPR was set up essentially with uh, focus on fusion technology. And that's the major and long-term goal. Quite like the thorium being the goal for fission energy, but we tend to do many other things in nuclear energy. And I think there is exact parallel to my mind that you have focus on fusion energy, but then you leverage technology in, and not only technology, the entire science and technology with the broadest view of wherever one can make a contribution. And it's also very nice that concurrent with activities in IPR, you have this facilities sitting right in an industrial area to look at industrial applications of plasma technology. And as Dr. Chaturvedi just now said, that there are a whole range of applications, and there is a large experience here. And now, obviously, there is a lot of industry interest in making use of these applications. I'm actually looking at this board. The biomedical application was actually something we've been doing it for a fairly long time. I think it's already in industrial domain. But gasification is another important area, and you can think of a variety of applications, including, of course, you don't require plasma for gasification of fuel substances or coal. But I want to mention this more in the context of the science involved. The coal gasification is a very old technology, but application of coal gasification, which has many important applications, for example, in fertilizer and many other chemical processes. But it's only now that we are having some breakthroughs in gasification of Indian coal, high ash coal. And there are several cases where, for example, we had our own heavy water plant attached to the Talcher fertilizer plant. And that fertilizer plant was based on gasification of coal, and that never worked, in spite of the fact that that technology was sourced from outside. And because that plant didn't work, we had to virtually abandon heavy water plant Talcher after completing it fully, resolving the problems in the process that was involved because it was a biothermal process. And so the point I'm making is, again, emphasizing what Dr. Chaturvedi said, that while there are many aspects of technologies which appear like more of an art than science, and in fact, traditional steel making, old one, not now. Today it is gone are those days, but it has been always an art, just like cooking is an art. It's a process, very important process, but you may know the science fully, but still. But uh, in terms of actually making use of these technologies, the science of it is extremely important. And I want to just highlight that example because we didn't pay attention to science involved in gasification. I think this nation has suffered. So, in that context, what you have here, uh, an excellent combination of people who have insights and who can find solutions to several plasma technology problems, leveraging the science that they understand they can leverage. And of course, by just doing science also is not enough. You may have developed the best of understanding, but technology is beyond science. And so you have the plasma, the, the facilitation center here for industrial plasma technology. And I think that's a great synergy between the two kind of activities, which are, of course, very strongly interrelated. Uh, and then in terms of applications, of course, looks like there is no end to it, including I know in old times there used to be a lot of interest in finishing the the uh, the things like door handles and knobs and very artistic finish leverage in plasma. Uh, I think in terms of processing textiles, wools, and other materials and fiber is another area where there could be a lot of market advantage if the technology goes in a big way. And then, of course, the treating biomedical waste. There are several processes, particularly when it comes to handling minerals which are hard to leach, where plasma plays a very important role. So this list is actually endless, and it's only important that we explore as many applications and this will be a two-way process. You may have to create awareness on part of industry about the potential application. So you need to demonstrate that to them. So there is a technology push, but you have to also create a technology pull, and through that, it's only you should create only push, and industry remains in the role of doubting Thomases. Then I think this translation will never happen. And so one has to work with industry, and industry must be able to see the benefit in terms of specific applications on specific products of interest to them. And it's only then you will create the pull, the technology pull. And that is where this translation will happen in a more effective way. And I think you have the right infrastructure to be able to do that. Now, there is also, of course, a question of cost. There are, of course, one can claim as a user or as a industrial entrepreneur that while there may be differences in terms of the end product, but then in terms of actual applications, there are pros and cons. So there are different processing technologies. Plasma is one of them. And so the cost effectiveness, you get some end result but at some cost. And even if you get very fantastic end results, in some cases it may be inevitable. There may be no other alternative. Even then, I would say cost effectiveness is an important thing, but still you will have a market because there is no alternative. But I suspect in most of the cases, these are evolving things. So there are alternatives. Plasma perhaps gives a better alternative, but it will create or it will get greater acceptance if there is cost competitiveness. And we must recognize that plasma is an energetic process. Creating plasma requires energy. And of course, apart from the capital cost, there is that running cost. And so, both in terms of making the most efficient use of energy, and also in some cases, it may be possible to recover some of these energies to minimize the energy cost. These are also extremely important aspects. As long as that cost competitive element is not there, it's different. Then you can only do the science, do the technology, and say that technology works. But for it to work in the marketplace, you have to bring in that element, and that's another aspect that we need to recognize. Of course, this meeting is specifically on applications in space and aerospace. And as I said, I don't want to talk more about it because Dr. Kiran Kumar is here. But I remember, because there is a small plasma activity in BAR, I remember we had a good collaboration between Department of Space and BAR to set up this high power torches to create conditions for re-entry vehicles at that time. There are also a lot of other applications where reverse, that is, you use plasma to condition the surface, coat the surface, and there, of course, I began my career not exactly using plasma but flames, and later on there was another division which was actually using plasma in terms of creating ceramic coatings. So, so I have some hands-on experience in coatings, and also I quite understand the challenges involved, particularly in coating highly dissimilar metals. So, Sir John reminds me of some conversation which I didn't remember, but there is that issue whether you can coat anything on anything, and that also is a subject of a lot of understanding, because what happens at the interface is extremely important, and that is true whenever we deal with dissimilar materials, whether you use plasma or any other method for joining or building one surface on another. I in the end, I only want to say that the synergistic working together can lead to very high quality technology products, but it can also lead to very high level of contribution in basic science or applied science. And I'm happy to see In fact, I was going through the papers that are going to be presented here, and I see a very diverse setup, including a few. Uh, I think there are some private industry or industry startups engaged in space, which was a very good sign. And I think if India has to be competitive, uh, we must build technologies which are globally based, and we must build technologies which are not only globally based, but we do that even in the domain of technology. There should be some newness which we do ahead of anybody else, and that is what really gives us the leadership position. So I think while we must get full mastery on technologies that are being worked by other people, other countries, but we must go beyond and build the technologies which are first time ever, at least to start with, done by us. And I think more such instances you can uh, we can bring it in our fold, faster will be the rise of our country to the top of the table. And it is these high technology endeavors that uh, that are really important in propelling the country in that direction. Anyway, we are here to discuss the plasma technology applications in space and aerospace. And let us put our heads together, let us put our acts together, and make sure that uh, we become the best in the world in this particular domain. Thank you very much.
Thank you, sir. We also have with us Shri A.S. Kiran Kumar, Vikram Sarabhai Professor ISRO, and a member of Space Commission, Government of India. Shri Kiran Kumar has steered the implementation of the application-oriented Indian space program, which has facilitated rapid development of the country in many spheres of Earth observation, communication, navigation, space science, as well as the development of indigenous launch vehicles and related technologies for providing assured access to space. Further, his role in the success of Chandrayaan-1 mission and Mars Orbiter mission has been significant. With these words, may I now cordially invite Shri A.S. Kiran Kumar to kindly address the audience.
Good morning to all of you. Shri Kakodkarji, Professor John Chaturvedi, and all of you who have gathered here today for the two-day interaction on plasma for space and aerospace. Today, if you look at where we are in India, after decades of technology development in space, where the country showed with the great stalwarts, starting from Vikram Sarabhai, Baba, and people like Kakodkar, and many others, India took up this task of making use of a disruptive technology in the 50s, for example, space, going to space and doing some activities from space was more disruptive than many of the disruptive technologies which we hear. And India took up this challenge with the great vision of Sarabhai and Baba on how India can take advantage of space technology and build capability in the country. You can imagine we were just 10 years after independence in 1957 when the first object went into space. And at that time, using this technology of going to space, how it will benefit the country if somebody were to convince the powers that matter, it would not be an easy one. But then we had such great visionary people. And over last many decades, what India has shown is to the world unlike others who started space program with the military activities as a prime intention, India was the only country which started space program for civilian application. And today, what India has shown is how this space technology can be used for whether it is dealing with cyclone or even bringing communication, broadcasting. Probably many of you may not be aware, way back in 75, India conducted one of the world's largest socio-technological experiment of beaming signal from a satellite borrowed from America in 2,400 villages, and then through that demonstrated to the country that it is the space technology that is the way to go for rapid development. In any way, there during the last 5 to 6 decades, where we have reached is we have our own launch vehicles, our own satellites, and we have demonstrated that this technology of space can be used for communication, broadcasting, navigation, and also space science, where it's also shown that you can reach to moon and Mars with very limited whatever capabilities that we have established. And not only that, it has also shown that these technologies, while we are using it for our own requirement, we have also made use of it for putting satellites of other countries. So far, more than 400 plus satellites of other countries have been put into orbit. And today, India has developed a technological capability of reaching to space and doing this activity. While capability existed, capability has been demonstrated for a country like ours, which is growing both in economy and which aspires to reach the top of economy in the coming decades. The only way it can move forward is make the most of all opportunities that are there. Today, human beings are looking at space as the fourth frontier. That means after conquering land, ocean, and airspace, enterprises or humanity across the globe is now looking at space, space tourism, space adventure, space habitation, you name it, everything is happening. And more private entities are getting into the space business, conquering space. And here we have already seen that private enterprise is doing entire space program outside the nation states. In the earlier era, it was only the nation states which could get into space and do activities. But today, what Elon Musk or Jeff Bezos have shown that you can do space activities totally outside the states and governments. Then space economy, we are talking of almost $1 trillion in the coming years. If India, which has established a tech capability in space, should it remain outside the space economy, or should it take a significant portion of the space economy and contribute to the nation's growth? And it is in this context that what you are seeing, that the government has made significant changes in the way the technology can be utilized in the country, how private enterprise can participate, and also do various activities in the process, not only enable the country for better standards of living, but also enable the country to grow economically. And in this context, you have also seen the efforts of last few years. Just probably a few weeks back, when India launched 36 satellites of OneWeb and Airtel, what it demonstrated was that the Indian space technology capability is live and ready to actually take the opportunity. What happened here was Russia, actually 36 satellites were sitting on a launch vehicle in Russian launch pad when the Russia-Ukraine war broke out. And when this happened, the company which was actually using these satellites for launch, between them and Russia, there was a split, and Russians said, no, we cannot launch this for you. So India, there was an opportunity for others. India took up this opportunity, and in a matter of few months, took the risk of ensuring that these are put. And today, what has happened is those 36 satellites are operating in space. In the same way, just a few days back, when you saw a private company doing a suborbital launch, what it also shows is there are companies in the country who are actually visualizing how they can provide launches to international community at a very cost-effective manner. And the first such thing has happened. Then beyond that also, if you look at, there are other companies which are building 3D printed engines which are much ahead of what even ISRO is planning to do. So the advantage of private enterprise is their dynamism and readiness to take risk, and because of that achieve success. But then that is where the country is heading, not only in space, but we also see in aerospace the number of aircraft that are being designed and the way aircraft industry is taking off. The environment is very, you can say, apt or prime is pregnant with opportunities. And it is here that those who develop the technology in the country not only make sure that these technological capabilities are provided access to by those who can convert these technologies into practical use, and not only that, earn returns out of that and grow forward. And it is here that both Department of Atomic Energy and Department of Space, what they have done over many decades is primarily look at developing those technologies for which we do not get access, or whatever is available, take that, and beyond what is available, make sure that you develop indigenously, and then through that bring in applications which are very different from what others have looked at. I would like to just give a couple of examples of how, for example, India looked at the technology and bringing in solutions. First one was, like I already pointed out, when in the 70s, while Americans were building the most advanced technology satellites, it was Dr. Sarabhai who convinced the Americans that they should allow us to borrow the satellite and move over India and conduct the world's largest socio-technological experiment of demonstrating how broadcasting can reach to people in the country. And you can imagine at that time, if India were to use the existing terrestrial technologies, not only it would have taken a long time, but also it would have required a lot of money to be spent. In the same way, in the mid-90s, India were able to provide to the global, in civilian domain, higher spatial resolution imaging system. And as a result of that, almost 18 countries' ground stations were set up and data being received from satellite. And even in navigation, if you see, we adopted the approach of building only 7 satellite constellation to meet the requirements of India and surrounding Indian borders up to 1500 kilometers, unlike what Americans, Russians, Chinese, or even Europeans did, 24 to 32 satellite constellation. And today, you will be happy to know that a small gadget, which is battery operated, can be fitted into the boat of a fisherman. And fisherman, when he goes into the ocean, he gets through this a mobile in his hands. Mobile does not need any connectivity to terrestrial tower, but this mobile communicates with the battery operated gadget fitted on the boat through Bluetooth or Wi-Fi. And an app on the mobile shows him where to go for fishing, in which place in the ocean he gets the fishing. Not only that, in his mother tongue, he gets alerts if weather is going to be unfavorable in the coming days, or if he is approaching international boundaries. So here you can see an example of a person who does not know reading or writing, taking advantage of the most advanced technology of launch vehicles, satellites, applications for his livelihood. So what I'm only trying to tell is that technology development is not being done for the sake of technology itself, but for bringing solutions to the problems we are facing. In the same way, we are also quite clear that the way India faced the problem of COVID and the way it enabled not only its own citizens, but also the global citizens, how it helped in COVID time with the science and technology that was available in this country and how it was put to effective use. In the same way, you are also familiar in the arena of digitalization, how India has made a difference and how India is actually trying to overcome another round of colonization that is happening today. Probably in the first round of civil industrial revolution, we missed that opportunity because we were being ruled. But today, if you ask, is the situation any different? Probably we need to think about it. While in the first case, physical raw material went out of this country and finished products came back and people exploited by selling the finished products at higher price. Today, probably what is happening is the intellectual capability is the equivalent of physical raw material, and the products that are coming out, whether it's in the form of social media things or devices like mobiles, etc. This is another round of colonization is happening. But in all this, it's only the thought processes of this land where the entire living on planet Earth depends much more than just technology progress, etc. That is a thought process which is very different, and that is a solution for future, whether you look at climate change and many other aspects. And it is here that we have a responsibility. That responsibility is we need to develop technology, because it is only the technology which can bring solutions for many of the problems we are facing. For a country of 1 billion+ people, meeting the energy requirements, meeting the various other requirements requires solutions which are more and more cost effective. If that has to happen, it's only those who are capable of grasping not only this technology, but also putting science to newer uses, that will make a difference. I'm extremely happy to see that this particular conference itself is coming at a very appropriate time, because today you are seeing more and more private companies entering into space. And when you are looking at the opportunities in space, whether it's humans in space or even going for interplanetary or long distances in space, whether it is plasma thrusters or other means by which using atoms, and even, for example, probably people will be looking at with today's technology, we can reach Mars only in 10 months or 9 months of one-way travel. And then the speeds at which the vehicles move are very inadequate. If you want to do it in a shorter time, you need heavier thrust capacities. And then that is not only the one, and also the possibility of using whatever material that is available in the interplanetary space. Is there any material that is available which can be harnessed, and in which case you can pick up your energy sources on the way of interplanetary travel? And this is again an area where there is a tremendous probably future people are looking at. Can we pick up material during the small fraction of maybe femto or attoseconds, where you have got particles which are getting generated, picking them, harnessing it, and then using them for movement? So there's a tremendous opportunities are available, and what is being attempted by bringing people together to forums like this, showcasing what we have already done and how things can move. And I'm also seeing that there are companies already set up in the country which are looking at how propellantless propulsion system is to be done, or plasma based or even microwave based systems being done for plasma, means for thrusters. There is a host of opportunity available here. And I would really compliment Shashank ji for conceiving of this idea of bringing all of you together and exposing you to what is happening in this, and also uh, setting the platform for future development. And what we have opportunity now is tremendous. India is among the few countries which are looking at small satellite or with a very low cost effective launch vehicles to be provided. And then both in terms of launchers, in fact, satellite manufacturing in Ahmedabad also, already one company has set up a satellite building company. They have started building satellites for others. And there is so much opportunity here. And making use of these opportunities definitely requires much more interaction, both interaction being open, being receptive to new ideas, and also not only being receptive, but quickly converting those ideas into practical use. And then, because as we are all aware, the life cycle of products are shrinking. While the product life cycles earlier used to be decades, now probably we are talking of maybe just a year or even maybe weeks itself. So we are all quite familiar with that. So in such a rapidly changing environment, if we have to be competitive and if we have to be effective, we need to actually conceive of things where we can get the returns in a very short time and move on. And in this context, definitely becoming more aware of what is happening is the essential thing. And then through that, I find looking at ways we can use these technologies for applications other than originally what it has been conceived for, is where the opportunity exists. And here again, we need to see in any new technology or in any developed technology area, if we have to make progress, we are actually dependent on that technology. And if we are making only incremental changes in that, can we be hopeful of outbeating those who originally formed? But it's only when we can think of something different using, that is where the original science, etc., comes into picture. And here is where the opportunity to get together, look at what has happened, and bringing it to users other than what it is being originally conceived for is where we can make a difference. And India is today at a very appropriate, opportune time for entrepreneurs to take advantage of the development that's happening. Government is trying to do on its part, bring in regulations and other mechanisms in a very effective manner, conducive for the industry to take. And of course, it is not an easy thing even for the industry. While the risks are there, returns are not certain all the time. And so maybe out of 10 people, few people only will succeed. But then those who succeed are the ones who will become the role models for others. So let me take this opportunity again to compliment Shashank ji for doing that, and wish all of you a great 2 days of interaction where you will know what is happening and use it in your own way. And all of this is with one aim, that India should prosper and people in this country should have better standard of living than what is there today. Thank you very much.
Thank you, sir. Now I would like to invite Dr. P.K. Atre, Chairman PSAA, to kindly address the gathering.
नमस्कार। मंच पर उपस्थित मुख्य अतिथि आदरणीय डॉक्टर काकोडकर, चांसलर HBNI एवं पूर्व अध्यक्ष AEC एंड सचिव DAE, सम्मानित अतिथि डॉक्टर AS किरण कुमार, विक्रम साराभाई प्रोफेसर ISRO एंड मेंबर अंतरिक्ष आयोग, विशिष्ट अतिथि प्रोफेसर PI जोन, पूर्व वरिष्ठ प्रोफेसर IPR तथा संस्थापक FCIPT IPR, डॉक्टर चतुर्वेदी डायरेक्टर IPR तथा भारत के विभिन्न हिस्सों से, अनुसंधान संगठनों से और इंडस्ट्रीज से सभी प्रतिभागी प्लाज्मा अनुसंधान संस्थान द्वारा आयोजित अंतरिक्ष और एयर स्पेस एप्लीकेशन के लिए प्लाज्मा पर आयोजित इस 2 दिन के संगोष्ठी में भाग लेने वाले प्रतिभागी, इन सबका स्वागत करते हुए मुझे बहुत खुशी की अनुभूति हो रही है। 2 दिवसीय संगोष्ठी अंतरिक्ष और एयर स्पेस अनुप्रयोगों सहित विभिन्न क्षेत्रों में प्लाज्मा के कई एप्लीकेशंस के बारे में जानने के लिए एक अच्छा अवसर है। IPR अंतरिक्ष क्षेत्र में संबंधित कई तकनीकों पर काम कर रहा है, जैसे प्लाज्मा थ्रस्टर्स, उपग्रह सौर पैनलों पर ESD परीक्षण, प्लाज्मा डायग्नोस्टिक्स, वैक्यूम तकनीक, क्रायोपंप, सुपरकंडक्टिंग मैग्नेट्स, कंप्यूटर सिमुलेशन आदि। उद्योगों को इस तरह के बुनियादी ढांचे प्रौद्योगिकी के ज्ञान की जरूरत है। इस सेमिनार में अंतरिक्ष और प्लाज्मा प्रौद्योगिकी पृष्ठभूमि के विशेषज्ञ अपने अनुभव साझा करेंगे और जो आगामी भारतीय अंतरिक्ष मिशनों के लिए प्लाज्मा आधारित प्रौद्योगिकी का पता लगाने का अवसर प्रदान करेंगे। इस 2 दिवसीय संगोष्ठी का उद्देश्य अंतरिक्ष और एयरोस्पेस के लिए प्लाज्मा अनुप्रयोगों पर ध्यान देने के साथ IPR सहित भारतीय अनुसंधान संस्थान संगठनों की कुछ गतिविधियों को प्रदर्शित करना है। वक्ताओं में विभिन्न अनुसंधान संगठनों और इंडस्ट्रीज के प्रतिष्ठित वैज्ञानिक शामिल हैं, जो संगोष्ठी के विषय को ध्यान में रखते हुए विषयों पर बोलेंगे और विषयों पर अपना विचार साझा करेंगे। हमें यह घोषणा करते हुए बहुत खुशी हो रही है कि सेमिनार में 200 से अधिक प्रतिभागी फिजिकली और वर्चुअली रूप से भाग ले रहे हैं। इन 2 दिनों के दौरान IPR और FCIPT प्रयोगशालाओं के दौरे के साथ साथ 14 आमंत्रित वार्ताएं होंगी। मैं संगोष्ठी की अपार सफलता की कामना करता हूं। आपका हमारा आमंत्रण स्वीकार करने के लिए बहुत बहुत आभार और बहुत बहुत धन्यवाद।
Thank you, sir. Now I request all the dignitaries on the dais to kindly release the book of abstract of PSAA 2022. Thank you all. Now I invite Dr. Suryakant Gupta, convener, PSAA, to kindly deliver the vote of thanks.
So, Namaskar. I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion. I, along with my co-convener, Dr. Mukesh Ranjan and Mr. Akshay Vaid, and on behalf of organizing committee of the Plasma for Space and Aerospace Applications, I would like to thank all the honorable delegates, both offline and online, who blessed us with their presence. I, on behalf of organizing committee, convey deep regards and heartily thanks to our honorable chief guest, respected Dr. Anil Kakodkar, guest of honor, Dr. Kiran Kumar, and distinguished guest, Professor P.I. John, for sparing their valuable time out of their busy schedule. And we are really enlightened by your presence, sir. We are thankful to our director, Dr. Shashank Chaturvedi, for his unparalleled support since the inception of this seminar. His continuous motivation and guidance has helped us to overcome all the difficulties in the way of organizing this seminar. We would like to thank Dr. Praveen Kumar Atre, Chairman LOC, for his unflinching support and coordination. We are thankful to all invited speakers for accepting our invitation. We have been fortunate enough to be backed by a very motivated and dedicated team. Our heartfelt thanks to all subcommittee members and IPR colleagues from accounts, administration, purchase, store, and computer section who have significantly contributed in various arrangements of this seminar. Thanks to all of you for making this event successful. Have a wonderful staying at Gandhinagar and enjoy the deliberations. I am sure all the participants and speakers will have highly enriched time for scientific interaction and discussion. Finally, I wish a very successful symposium ahead. Jai Hind. Thank you.
Thank you, sir. With this, we have come to an end of today's inaugural session. Now I request all the delegates and the audience to kindly proceed for a group photograph, followed by high tea, which is arranged outside the seminar hall. And soon after the high tea, we are going to start the first technical session. Therefore, I request all the speakers to kindly load their presentations during the tea break. And Mr. Kushagra Nigam, who is sitting over there, will assist you. And there are a few more announcements that the exhibitions related to space startups and MSME has been arranged outside the seminar hall. So all are requested to visit the same during the tea and lunch break. And there is one announcement for tomorrow that we have arranged a tour to IPR. So I request all the interested participants to kindly register their names at the registration desk for tomorrow. Thank you. हेलो। तो बहुत ज्यादा है, दूर खड़े रहना पड़ेगा ना। हाँ, वो एको हो रहा था तो मुझे लगा उधर हाँ, थोड़ा दूर खड़े रहना, थोड़ा दूर खड़े रहना होगा, ठीक है। Welcome back to the first technical session of PSAA. I request all the participants to kindly be seated, please. I request all the participants to please be seated. So now we are going to start the first technical session with a keynote address by Professor P.I. John, founder of FCIPT and former senior professor of IPR, who has graciously consented to deliver a keynote address today. Professor John held the Meghnath Saha Chair at the Institute for Plasma Research, Gandhinagar. He has contributed significantly to the growth of plasma physics in India. He is a fellow of the Indian Academy of Sciences and has served as consultant to the International Atomic Energy Agency, Vienna, and the United Nations University, Tokyo. He served as head physics section of the IAEA from 2002 to 2003. He was a member of the Science and Technology Advisory Committee of the International Thermonuclear Experimental Reactor Project in France and represented India on its council. With these words, may I now request Professor John to kindly deliver the keynote address.
Dr. Karkokar, Dr. Kiran Kumar, Dr. Shashank Chaturvedi, and friends. I thank the Institute for Plasma Research for inviting me back to FCIPT to celebrate 25 years of FCIPT and also to participate in the meeting on aerospace applications of plasma technology. I recall the exact moment when the idea of what would later become FCIPT came to me. In early 1990, we had commissioned the Aditya tokamak, and I was escorting Professor Ramacheshan, who was a IPR council member, around the tokamak. The tokamak is a very complex device with magnetic field coils, vacuum vessels, turbomolecular pumps, and diagnostics. And he said he was considerably impressed by what we had done and appreciated everything about the device and what we had done. Then he asked me how many people would be affected by what we did with Aditya. I had never asked this question myself. So I enlarged the ambit of the question. I asked how many people would be affected by what we had done over the years at PRL and IPR. affected directly. So I found that the answer to this was quite disheartening. People wouldn't much care what we did or do in a fundamental research program. And we say that the applications are lying in the future, sometime in distant future. And in fusion, the future is ever receding, as we know. People say fusion is around the corner. That corner is always receding. Now I am told that ITER would be delayed by 7 years. So Aditya, what is the impact of Aditya among people, ordinary people? And so this is very, very difficult thing to admit that what we had done, very substantial amount of engineering and technology, would have very little impact on average, ordinary people. So I had an epiphany, and the idea of finding short-term commercial applications of the plasma physics knowledge that we had acquired over the years, both at IPR and PRL, came to me suddenly, that we can say fusion is there, we'll deliver, but can we deliver something more substantial on a very short-term basis, something which will touch an ordinary person, like a housewife? Can we increase the sharpness of the knife that she uses using a plasma technology? Or can we make sure that the scissors last longer by hardening it or by treatment and so on? Things like that. One pet project I had was to make a plasma sterilization device and supply it to every kitchen so that the housewives could sterilize the bottles that she puts pickles in, or the baby milk bottle can be sterilized in a small device. So it's like a microwave oven, which is now there in every kitchen. We have a small plasma device, which should be there in every kitchen. So this is what drove me to consider thinking about plasma and its applications. Okay. So what applications can come will depend on what plasma has as its property. So plasma properties like the response to electromagnetic fields, high chemical reactivity, sheets, radiation, particle flux, and all these can find potentially interesting applications. And the application has to be integrated with the plasma material interaction and manufacturing process to deliver a technology. So both equilibrium, that what we call the hot plasma, and the cold plasma, non-equilibrium plasmas, can be exploited. So this is what set me on the path to starting FCIPT. And conviction arose because the plasma processing had very, very clearly demonstrated its potential in manufacturing silicon chips, for example, at that time, those days, 1990s. So it's becoming extremely important tool in high value added, high energy intensity applications. So when I approached Professor Kao with the idea of starting a plasma processing program, he was, as was his nature, very enthusiastic. The IPR Council gave a favorable nod to the idea of pursuing plasmas for profit. I remember particularly the support given by Professor Ramacheshan and Dr. P.K. Iyengar. There were no pre-existing models to this kind of activity in a fundamental research institute, and we had to develop the rules of engagement as we went on. So activity had to be unique because of this nature, that it is not something that is done in every research institute. So we cannot copy what is done in other institutes and implement here. We have to find how to go about doing this. And it had to be, it's unique because it has to be relevant to industry. We cannot create an application for its own sake. We have to find an application which the industry actually needs. So as Dr. Kakotkar mentioned earlier, we have to engage with the industry, find out where there will be an interest in an application. And industry is very difficult nut to crack because they are very down to earth, and we cannot give high promises and convince them, excite them. We have to actually demonstrate something, show them that this works, and then they will buy. So this is something that we have to learn. And the other thing is that, in principle, we can gain or lose money in an engagement, because a wrong development can actually lose the money that we invest in. So we are almost like industry in that sense, although it's working in a fundamental research institute. So the contractor-client relationship with industries also are, it's a very strange situation in a fundamental research institute. So the plasma processing activities took on a qualitatively different form when we set up the Facilitation Center for Industrial Plasma Technologies in a rented building in the industrial area of Gandhinagar in 1997. And there was a very clear reason behind moving to Gandhinagar. I remember sitting in IPR and inviting industries to come over and talk to us about what we can do and so on. But the grandiose structure of IPR, people have called it the Taj Mahal, and all those impressive infrastructure there actually was inhibiting industries to come out and talk to us. They said they are doing something very, very, very simple. You are sitting in this grandiose building, and what can you do for us? So there was a credibility problem. And I said, to make some impact, we have to move to at least an industry area, situate like an industry, and then talk to them, and then it will make an impact. That's the reason why lack of space in IPR was another reason. But fundamentally, we found that we have to be like an industry if we want to talk to industry. You cannot sit in an ivory tower and expect industry to engage with us. And FCIPT consolidated all technology development, demonstration, incubation, and commercialization activities. And we had a multidisciplinary group of physicists, material scientists, chemists, and engineers, and infrastructure process and instrumentation development. And we started there in 1997. The other thing that we did was that we said that we had to manufacture and supply complete reactors to industries. We cannot simply transfer a process to them. We have to show them how it's in a reactor so that they can switch it on and make it work. That is integral part of the technology transfer process. Financial self-sufficiency was a target right from the beginning. That's a promise I had made to the council, that will not be a burden, will not be a drain to the institute. We'll actually at least not make a loss. We'll make money to cover our cost. So FCIT has become a pathbreaker in India in converting physics-based research into commercially and societally valuable devices and processes in basic research organizations. Over the years, we have learned how to use the plasma environment to do various useful things. And that's what I am going to spend a little time, basically boasting of what we have done. And I hope you will forgive me for this pride in what we have done. We can nitride components ranging from precision molds to hydroturbine parts and reach defined hardness and case depth values. This is the case of a nitrided, the core material, the white layer, and then the nitrided layer. So we have built large reactors so that industrial components, either large in size or in large in quantity, because nitriding a single mold is very expensive. So you have to put at least 100 pieces together and make it work. So that's another technology that we learn. We put 100 pieces, very different from putting a single piece. Make them work in close association, in proximity with each other. It's a technology itself. So this is something that we developed in the beginning. And then we started a job workshop so that the industries in Ahmedabad, there's a lot of precision mold making companies, Cincinnati, Milacron, and companies like that. And they could bring their expensive molds to us and we would nitride them, send it back. And thereby, actually, we promoted a private company to set up a nitriding shop, plasma nitriding shop in Ahmedabad. We supplied the equipment. That the first reactor that we supplied to them was set up in a company in Ahmedabad, because he found the market which we already were exploiting, and he actually was able to take on jobs from them. So this is something that we did. Then we can synthesize optical quality, reflective and anti-reflective coatings over large areas with as high as 95% reflectivity using plasma-enhanced chemical vapor deposition techniques and using safe monomers. So in plasma CVD, in normal CVD, a lot of very, very poisonous chemicals are used for creating the coating. And here we can use monomers which are very safe. So its environment is also very safe. And again, to promote the activity of the brassware, this is the brassware manufactured in Moradabad. Moradabad is the big center for brass industries. And they came to us and said that they have trouble competing in Europe because in Spain, there's a company which does plasma quartz coating on the brassware. So they asked whether we could help them. So we developed a process of silicon dioxide coating on brassware after polishing it. And then that's a very, very thin layer, so transparent. And the coating is lifetime coating. Quartz is very hard, cannot wipe off quartz by polishing and so on. So we set up a shop in collaboration with Moradabad Brassware Industries and set up a reactor there, train people how to run the reactor. And within a very, very short time, that became viable because that is again a shop where the local industry, these are capital intensive equipment, very costly. So each small industry cannot manage to set up a facility in their own place. So a central place where people can bring the brassware they make, they can be coated and can be sent back. So this was a success story. And this was set up in with our involvement. We can deposit super hydrophobic fluorocarbon films on surfaces with pulsed DC, RF, and expanding plasma jets. And these are cold plasma. They're not, although it looks like a torch plasma, it's a cold plasma. You can actually physically touch it. Nothing will happen. Cold plasma, and it's ideal for plasma CVD. And super hydrophobic surfaces are water repellent. So there are many applications where that becomes very useful. And we actually found something very interesting, that to deposit this film, you need carbon tetrafluoride. And at those days, they had to be imported. And also there were about restrictions, and it's very expensive. And we found a innovative process of using Teflon waste and pyrolyzing the waste and creating CF4 out of that. And that was injected into the plasma, and then the deposition take place. So the raw material was free for us, not CF4, which is expensive. So that this became very useful. See this, sorry. This is a water droplet on that surface, 165 degrees contact angle, which means that it doesn't wet the surface at all. So this is applications like, yes. Oh, that varies, depends on I mean, typically kilovolt pulses, yeah. Yeah, can be 3, 4, 5, 6, 10. Depends on the particular quality of plasma that we want. They have to be kilovolt, nanoseconds. So that's the demand. Okay, so this is something that we thought was quite interesting. Then we developed plasma torches to create high enthalpy flows, to test materials, and to create high enthalpy flows for material testing, high temperature pyrolyze organic material, and assist the combustion process. So plasma assisted combustion is a very important field, especially in the context of space. We'll come to it later. And what we did here again, Dr. Kakotkar mentioned that we cannot simply copy something and sell as a technology. We have to innovate. And in each of these, I'll highlight some innovation that we brought in. This torch, when we built it for medical waste pyrolysis, we used a conventional plasma torch with a hot tungsten cathode and so on. And we found that it runs with nitrogen. And we found that the nitrogen cost itself is a substantial cost of the torch operation. So we asked ourselves whether there is a cheaper torch that we can make. And that is how we developed the graphite-based graphite cathode torch. And the advantage is that the nitrogen torch, you have to cool the anode very effectively, otherwise temperature goes up. We are talking of 10,000 degrees. Whereas a graphite torch, nothing has to be cooled. So there is tremendous saving in all the cooling technology, and also the cost of running energy cost. I mean, it's also very efficient. So we developed this graphite-based torches, and then we innovated further on that. The graphite torch uses nitrogen, and what gets pyrolyzed, organic material, becomes what is called the syngas, carbon monoxide and hydrogen. And that is energy gas. You can inject it into a internal combustion engine, it will fire. But when you inject the nitrogen into the torch, what comes out is a syngas plus nitrogen. So there is an expensive gas separation process to get the syngas back. And that's very, very, very involved process and expensive. So we ask the fundamental question. Now, pyrolysis produces gases. Organic material gets pyrolyzed, it becomes nitrogen and hydrogen and syngas, hydrogen and carbon monoxide. So why not use that gas to run the torch? So we created a process by which this gas can be extracted, cooled, and injected back into the torch. We call this torch an endogenous gas source torch, and we got a patent for this. So that's a great innovation, if you ask me, because it solved the problem of gas separation. It created economy because nitrogen cylinders are no longer needed to run the torch, and so that is our innovation there. Then we found a process of plasma etching brass surfaces so that the zinc gets released and the zinc reacts with rubber, and the rubber can be molded with the brass to produce the very common automobile tire valves. The valve is a brass rubber combination. It's a company in Mysore, which is a large manufacturer of this. So we developed this process, and here again, this is a valve. You are familiar with, every car owner knows that this is a valve, and this is manufactured in lakhs. So you have to create a process which can be scalable to that kind of capacity. And then again, we built a reactor, we made it work, and then it got accepted by industry, supported by the Department of Science and Industrial Research. And that is how the technology went out. Then we have developed cold atmospheric plasma technology. And with that, we made it possible roll-to-roll treatment of polymers and textiles in collaboration with Mantra and agencies like that. So that is something which is important for textile treatment. High heat flux in thermal plasmas can produce spheroidization and densification of ceramics. This is again an application developed for CUMI in Madras, because they wanted, they were producers of alumina ceramics, and they said they want free-flowing ceramic powders. And so we put, each one is a few millimeter in size, put it through the plasma torch. In transit, as it travels through the plasma, the ceramic material melts, and when it comes out, it recondenses, and spheroidal form is created. And this is another technology that we developed. And more recently, we have created technologies of low ion energy beam extraction from plasma sources for texturing surfaces, nano texturing of surfaces to create nanoscale patterns of implantation in solid state memory devices and other applications related to very high efficiency detection of Raman scattering or using surfaces, materials, and so on. Creating nanoscale patterns by ion beam radiation. This is a SERS-based detection of glucose with very low concentration. So the signal to noise improves substantially by using nano texturing. Very high frequency plasma CVD. The process enables high rate, large area deposition of device grade microcrystalline silicon hydrogen films. So this is very important. Very high frequency means the plasma, impedance become a real impedance. It matches it becomes resistive, and so the power absorption is very high. And the power absorption determines the density of the plasma. So if you go to very high frequency, you can create very high density plasmas, and hence the throughput of the process improves. And this is something that we have done, a device grade silicon, the microcrystalline silicon, hydrogenated microcrystalline silicon, which is like a solar cell material. So this was done. Then we developed plasma etching of Angora 5-inch. Increases the micro roughness. Angora is a very smooth wool, so you cannot spin it very easily. You have to create some roughness. And remember that wool, each fiber is, sub-millimeter size. So you have to etch the surface uniformly. And it has been done in atmospheric pressure. You cannot put it in a vacuum and all that. So here again, we created the technology, built reactors, and we set up this facility in Kulu, if I remember correctly. And that plasma, cold plasma that we developed could run without helium. We showed that we can create the same cold plasma conditions for etching without helium, which is a costly raw material to go in. And this facility was set up, and the wool farmers in Himachal area can bring their wool, come to the reactor site, get it treated, and take it back. So it's again a successful technology that transferred to actual uses. Cold plasma for biomedical applications. This is something which happened after I left FCIPT. So if there is any fault in the technology, you don't blame me. So, but this is very nice. You can actually create this cold plasma streams, and you can let it fall on your hand. Plasma is considered to be very, very energetic, but nothing happens to your hand. And actually, it's being used for treatment, cancer, treatment of skin, and so on. This is an area where application is running ahead of science. People say it works, but people don't understand why it works. There's a whole lot of research. There's even a journal for plasma medicine publishing things. So this is like many applications which runs. I'm told that steam engine, when it started working, nobody knew the thermodynamics. So steam engine worked, and the thermodynamics, which is the science behind steam engine, came later. So plasma torches for skin and body application is a field like that. And the science is waiting to be developed, and people are working on it. And we make these torches, we sell the torches. Anybody can buy the torch and use it for various interesting applications. You can create things like a plasma treated water, which apparently has a market, and plasma for agricultural treatment and so on. So these are all possible. Then this plasma pyrolysis for medical waste, it was developed under TIFAC DST project, and first unit was set up in Goa Medical College in 2004. It's been set up in many places, and now I'm told that a huge 100 kilowatt unit is being used to set up a facility in Benares for medical waste treatment. And I congratulate people behind that, because running that for many days continuously, it's a real demonstration of technology that you can scale up to that kind of sizes. So let me then come to before I go there, let me come back to this point of innovation. And I'm very happy that whatever we have done, we have actually taken the process or the development forward through our input of plasma physics knowledge. And that's quite satisfying. Although we cannot claim to have invented path-breaking inventions of technology, but I think we have innovated, which is very satisfying for a scientist. But this effort on innovation must continue, because without that, we will be replicating all the other technology. So if we create our own technology, we have to innovate. That's very important. Okay, now extending our plasma physics knowledge to space program started with the indigenization of the nitriding of solar panel drive gear of ISRO satellites, which was previously being done by a British company. And I think ISRO had some problem during some period of getting the services from British company. So we built a space quality nitriding system in FCIPT. We started supplying gears nitride in our facility. And I remember we had very little problem in getting the nitriding done, but we had tremendous amount of problem with packing the material, sending it back to ISRO, because they have very, very strict instructions on how to pack, and they put all kinds of stuff inside so that it doesn't. So difficulty was in packing and forwarding rather than nitriding. So we created the acceptable case depth and hardness and so on. And later on, we supplied a space quality nitriding system to ISRO, so that this packing and forwarding was no longer necessary. They could do it themselves. So this facility was sent to ISRO. This is the quality of equipment supply that we do. Industrial grade quality, good aesthetics, operational, all those ergodic design, things like that. All computerized, advanced system control and everything, automated. So human intervention is not necessary. You switch it on, it runs, and then switch it off. So that's the quality of instrumentation that we have been able to provide. Then the second intervention with interaction with ISRO happened in 2004. I had a conversation with Dr. P.S. Goyal, who was at that time the ISAC director, and he made me aware of the problem faced by ISRO on the failure of solar panels on the satellites due to arcing. Satellites in orbit are embedded in a plasma environment, and the charging due to energetic electrons create very high voltages. And these voltages, remaining there for a long time starts arcing process, because arcing is a time-dependent breakdown is a time-dependent phenomenon, and the glow to arc transition is time-dependent, and prolonged high potentials lead to arcing. So he said, we do not know what is happening inside. Can we find out? So we set up a facility which we call SPIX, the Space Plasma Interaction, Satellite Plasma Interaction Experiment, in which we simulated the space conditions by putting the solar panel in the plasma environment, and we injected electron beams onto the solar panel, charge it up, and then arcing would develop, and we would have diagnostics to look at how the arc develops in time, in space, and things like that. And we began to understand the physics of this, and we proposed, and then the arc initiation development were measured with Langmuir probes and so on, CCD cameras, current transformers. The data received were analyzed and used in a model, and the experimental data created insight on the physical phenomena generated from the modeling. And then we made recommendations to ISRO on how to improve the surface conditions so that arcing will be inhibited, not prevented, but can be reduced. And ISRO implemented them, and apparently that worked, improved the life of these satellites. And that is, again, second time we interacted. And this is a SPIX facility which we set up, all the instrumentation behind that. Sorry. Oh, it's okay. So this is SPICS instrumentation, and now the SPICS 2 has come up in 2008 to simulate the geosynchronous Earth orbit conditions. And it also meets international standards of data accumulation, acquisition, and so on. And so this is a continuing interaction with ISRO. Then I suggested to ISRO at that time that we could actually develop the Hall thruster for ISRO. I remember I had a conversation with Nathaniel Fish, who was a plasma physicist at Princeton Plasma Physics Lab, which had an activity like FCIPT, and he was involved with developing advanced Hall thrusters for NASA. So I found that there's a lot of physics there in the Hall devices, and since we were plasma physicists, we claimed to ISRO that we understand the Hall thruster more than they did. But they said thank you, but they developed their own Hall thrusters. But the interaction continued, and when the ISRO developed the thruster, they said they invited us to diagnose the thruster plume. Thruster is this inside, and it emits a plasma plume, plasma jet, and that is what creates the thrust. And they wanted us to diagnose this. We went to Bangalore, set up the facility, did all the diagnostics, and that is a very satisfactory interaction. But the invitation to ISRO to develop thrusters still stands, because there is a very interesting thing about technology. A technology is additive, combinatorial. You can take technology A, combine with technology B, and you get technology C. So I wondered whether Hall thruster has a problem that it uses xenon, which is a very expensive gas. Can we find a cheap alternative to xenon? We cannot use argon and all because the mass is low, small. You need heavy replacement of xenon. So I have an idea of using a metal vapor driven Hall thruster. I searched the literature, nobody has thought about this idea. We can develop it. Metal vapor can be produced by cathodic arcs. If you put a wire in a vacuum and apply very high negative voltages, it begins to run an arc, creates metal vapor in plant. We do it a lot in coating applications and all. I had a PhD student who was working on metal vapor plasmas and so on. So we have some knowledge, and it can replace xenon in a Hall device, and that will be unique Hall thruster driven by metal vapor. And one of the problems xenon is it is gas, so compressed to high pressure and stored. The volume, material to volume ratio is very low. Wire produces as much. A single wire will produce as much xenon as in a as much metal vapor as in a xenon pressure cylinder. So it's very easy to store. Storage becomes very easy. So that is something that we could think about. And now, I'm not an expert on aerospace and plasma space applications, but there are some areas in which we can work together. Some areas which I understand on the long term would be important to ISRO. And one is that this is when you are thinking of planetary projects, going to planets and so on, there are restrictions on protection of the planets from earthborne virus and all that. So the space, anything which goes there have to be sterilized. And you can sterilize a space vehicle by putting it into a steam bath and so on. So you have to think of cleverer, cleaner ways of sterilization. Our technology of cold plasma is an absolutely good sterilizer. We developed it initially in collaboration with Johnson & Johnson to understand their plasma sterilizers, diagnosis, and so on. So we have a long record of understanding plasma sterilization. We have built plasma sterilizers, and we could work with ISRO in adapting cold plasma sterilization for space related components, for planetary missions and so on. That is something that we can do. Then the other important thing is that in scramjet, the problem is that it operates at very high atmospheric height, so pressure is very low. So the scramjet flame is very unstable, because one thing is the flame spends very little time, few milliseconds in the combustion chamber, and it goes out. So to stabilize the ignition, people have started using plasma to make that ignition stable. And that is something that we have experienced in plasma torches. Adapting it to place plasma in space or scramjet conditions would be a relatively easier task. And so that is another area in which aerospace application. Then the third is in the development of microthrusters. So there are all kinds of, as Dr. Kirakuma mentioned, small satellite sizes are going down. So the station keeping and thrust and all that can be provided by smaller and smaller plasma thrusters. Hall thruster is already well developed, relatively well developed, and with specific impulse and thrust. And there are all kinds of electrothermal, electrostatic, electromagnetic, Jakrosvik accelerated thrusters and so on, pulse plasma thrusters. So that is an area in which we could work together, look at what is required and how it can be developed and so on. And of course, he also mentioned the Mars mission would be substantially reduced in time if they employ engine which is making a lot of news is the Basimer, which is create 50 kilometer per second speed for the rockets. So Mars mission is supposed to come down in a few weeks rather than many months. So this is a this is being developed by a private company in the US. It is a what is called variable specific impulse, and it is a plasma source created by Helicon plasma sources. We have a lot of work done in IPR and Helicon plasma sources. We have the know-how there. And then it is energized, heated by ion cyclotron heating. We have, again, a lot of experience ion cyclotron. In fact, we are supplying the ion cyclotron heating power supplies to ITER. IPR is the supplier. So we have a lot of experience in this. We have also done experiments in tokamak on ion cyclotron heating. So component-wise, each technology component has an experience foundation in IPR. That's something that we can collaborate. And the point I'm making is this kind of meetings are excellent to exchange ideas, create new ideas, and brainstorm, and then come out with possibilities which are not explored. And our strength, combined strength, we can be very productive. And that is what I would like to conclude with, that message that we should collaborate and succeed. Thank you very much. Voyager speed is about 20 kilometers per second. So, how do you coordinate this speed in terms of digital material and space info? No, say that again. What is the question?
Yeah, the question is, sir, like if you see Voyager, which is, I think, reaching end of the galaxy. Okay. So the speed,
In what time?
20 kilometer per second is the speed
Yeah,
maximum.
but what it acquired that speed in what time? Very, very long time.
That is okay, sir. But
Yeah.
50 kilometer per second, no? Whether are we be able to achieve those speed, and what will be the end state between your
No, the problem is very simple.
yeah,
Thermal exhaust has
okay,
a limited speed, okay?
okay,
Few thousand kilometers per. And when you go to plasma exhaust, you're now considering temperature, effective temperature, which are 100 times that.
okay,
Okay, so the plasma exhaust velocities are kilometers, 100,000 kilometers per second. Okay,
yeah.
and so that is what ultimately will give the reaction speed to the rocket at this to this kind of velocity.
But we have to also look at the actual things which is moving with that speed, no? Material per se.
Everything is moving at that speed, so it's a stationary system.
Okay.
I'm not claiming to be an expert on this, but as I understand this, these engines are being developed for the specific purpose of reducing the speed to planetary missions.
Good afternoon, sir. This is Sunny here from Star. So I have a question that we have seen that plasma nitrating have shown a very good effect on metals where it increases the strength. But do we have any research done for any composite materials where we have done plasma nitrating for CFRP, let's say, and any increment in the strength of CFRP? Have that research been done in India so far?
No. You have to have a nitridable species in the metal.
Yeah.
The when plasma nitriding is done, it's chromium, which gets so unless you have chromium in the steel, you cannot nitride. All steels cannot be nitride. So you have to have chromium.
Okay.
So your plastics cannot have that condition.
Not
Right.
just about the plastics, but any other alloys I was talking about. Now I got it
Alloys,
right.
alloys have been nitrided.
Okay.
Alloys with the specific chromium presence have been nitrided.
Okay. Thank you.
And there are a lot of these in there are substandard quality. So they're going to be very quick. Is it possible to get the reconditioned by corporate? So I think it's a huge expenditure simply because of good quality. Plasma nitride is probably cheaper compared to other materials.
Well, I don't. Yeah, probably on the large scale, the cost can come down because advantage plasma nitride you can scale up the system with very large quantities. So the number of samples per hour can be large, whereas metal deposition and all that is you cannot scale up like that. Okay. Yes, sir. Let me tell you that we had very, very good interaction with the National Hydropower Commission. They came with the problem that the hydropower component, our guide rains in Himalayan rivers were eroding because of silica. So we actually had a long time program of nitriding them, testing them in actual operation. We even got a company involved in actually because quantities were very large, we could not do it. It's a very successful project. And the worn out parts we could recondition by metal deposition and then again nitriding. So this is the Alfonso can give you more information about.
But this is not just understand of it. Most of the line.
Right, I understand. Yes, yes, yeah. Yeah. Why I'm mentioning hydropower commission, because that's an example which is very similar to this. The hydropower component, I was amazed, would be eaten away in a few months' time. Larger estate. So that's something that's important. We had a very good collaboration with a Baroda-based purpose diagnostics industry, which verified all our results, and that is a good program. Except we broke up because they wanted us to set up a huge nitriding facility in Himalaya, and some company. Yeah, actually, I was told that Sia Brown Brewery had a plan to set up a facility, but it somehow didn't succeed. But then we parted not in very friendly terms with the Hydropower Commission, because they said we are not helping. But in principle, it can run to a third party.
Good morning, sir. My question is regarding plasma ion implantation facility.
Yeah.
So I want to know that with this facility, can we do texturing of metal surfaces inside the 3D electrodes?
Inside?
Inside 3D electrodes. Some cylindrical and conical shaped electrodes are there for TWTA tubes. So we want to do texturing inside that tubes component. So with this facility, can we do this?
Are you asking whether we can implant inside the tube?
Yes.
Yeah, we can implant inside the tube.
Okay.
Inside cylindrical tubes, we can implant.
Okay.
In fact, that's again another innovation which see, when we started plasma ion implantation with the Indo-German collaboration surface engineering, we started with 50 kilovolt ions, actually shoot into the plasma. Then Dr. Mukherjee and I thought, why do we need it? We can help the implantation by heating the sample. So we developed a process which we call shallow implantation and diffusion hardening, SID process. It's a patented process, and that actually is a marriage between nitriding and implantation. That's a new technology. As I said, new technologies come by marrying new. So SID is a product of marriage between plasma ion implantation. It is very energy consuming. High volt 50 kilovolt power supplies are very expensive, and they have to pulse. So lot of technology. And heating is relatively cheaper technology. So SID came out of that kind.
Sir, actually, cow milk is being popularized nowadays because of the health benefits. And there are many gausalas. They are supplying the cow milk with help of glass bottles. They have a problem of washing, not proper washing is being done. So can we use plasma for sterilization of such bottles, and how economical it is?
Well, we did a case study for somebody in Baroda who was manufacturing plastic tubes for blood collection. Blood collection tubes had to be sterilized every time. We did the actual case study and found that it's economically done on a large scale. Each tube you cannot independently do. You have to do it on a mass scale. And so it's possible for doing it on a large scale. Sterilization technology is available. Scalability has been proved, so you can actually demonstrate it.
Plasma activity for making super hydrophobic. So using the chlorine gas, we are coated. So it is a coating or it is a nano
Nano coating.
nano?
It's a coating. The coating actually develops a texture automatically without doing anything. So when you deposit this film, the film condenses into nano project. So this is what actually gives the super hydro. It's like the lotus effect. The surface has nano structures. So here the surface develops nano structures on its own, and that's how it becomes.
And this happen on a metallic.
Can be done on any metallic, non-metallic. Yeah, it can be done. Yeah, cleaning the. Yeah, we can do it on. Glasses with self-cleaning property are already commercially available. Yeah, but yeah, it can in principle can be done on you can actually do the coating on the, so that's very yeah.
So let's thank Professor John
Thank
for the
you.
nice talk. So we have our next speaker, Dr. Alfonsa Joseph from IPR, and she is going to deliver talk on an overview of plasma in space and aerospace applications. So I request Dr. Alfonsa to kindly deliver the talk.
Good morning. The topic on overview of plasma in space and aerospace will briefly touch upon all the topics that we'll be covering in today's and tomorrow's lectures. So I will not be able to go into the details of each topic, but yes, I will be telling you all the activities that we do in IPR. As you all know, that plasma, there are two types of plasmas, cold and hot plasmas. Hot and cold plasmas interact with the material in different ways. And because of that, there are a lot of applications based on these plasmas. And at this center, as well as in IPR, we work with many applications which are listed here: textile, health, hard coatings, agriculture, communication, waste management. And today, the topic of our discussion here, space and aerospace also. So the first thing that comes into our mind when we talk about space is a satellite. So yes, this is a picture of a satellite. It has solar panels, and the center you see the propulsion and the various components attached to it. So we thought that let us use these plasmas to cater to some of the problems that are associated with the parts of this satellite, and also to improve their functional properties. So we tried some work on antennas, on solar arrays, as well as thrusters. So all these programs or all these activities cannot be done without the help of our ISO centers. And so together, joining hands with them, we worked on with various programs. The first one with IISU, that is ISRO Inertial Systems Unit in Trivandrum, where we worked on improving the life of their spacecraft components, that is bearings and kinematic parts, to improve the service life. Second, we worked with ISIC before and now URSC on solar panel, that is on their charging problems associated with solar panels. We also did titanium coatings as well as plasma nitriding with the help of SAC. That was for the kinematic parts and also on the bearings. We also did some coating with SAC for the antennas, that is polymer-based antennas. With the help of LPSC and VSCC, we did some programs on thruster plasma diagnostics and material characterization to study the anode liner erosion on plasma thrusters. So coming to the first problem that was done with the help of SPIX project, We all know that solar cell is very important for spacecraft because it needs power to run the sensors, active heating, cooling, and telemetry, as well as for electric propulsions, and they're all rectangular shaped components. Now, these are immersed in the space environment, which contains lots of electromagnetic radiation as well as ionizing radiations. And this then gives charging to the spacecraft solar panels because of the space radiation, UV rays, atomic oxygen, as well as discharge arcs. So if you have such arcings on these solar panels, they result in damaging the electronic components, destroying the sensors, as well as special control coatings. It also spoofs up the attitude control systems and so on. So for this, it is very necessary to create a space-like environment in the labs. So we at IPR have established a test facility that can create the same space-like atmosphere in the vacuum chamber, and we expose the solar panels to them and try to study the arcings as well as to find out mitigation techniques on the solar panels so that we can stop those arcings. And so we have a talk by Dr. Suryakant Gupta, who will be talking on this indigenously developed test facility. The second problem that the plasma thruster in a space satellite is about the erosion of the anode liner. Now, these occur during long operations, which leads to faster erosion of the material, changes in the magnetic permeability, localized heating, and even the breakdown of the ceramic, as well as surface flashover. These problems were attended to by coming into an MOU agreement with LPSC and various objectives for measuring the erosion rate, measuring the magnetic field, and the permeability of the magnetic material and electric parameters were studied. Recently, we also had a project with VSSC to study the erosion rate on a newly developed anode liner, which was the boron nitride. And it was observed that our studies helped them in selection of this material. And this material has been now selected and it will be now used for their TDS, that is Technology Demonstration Satellite 1, for the mission of PSLV C-54. More details will be delivered by Dr. Mukesh Ranjan just after my talk. This process of plasma nitriding, which we developed for IISU, has been talked from morning. And in this process, you can see the actual plasma, which looks like a purple glow color around the gear components. These are actual gear components being nitrided. These materials are called 17-4 pH, that is precipitation hardened martensitic stainless steels. And their main aim was to increase the hardness for improving the wear resistance. And we were able to increase the life component. So as Sir said in the morning, that packaging was a real problem. So whenever they wanted the gears and pinions to be nitrided, 2 people used to come with them and stay here till the process got over, and then took back the components because of this packaging problem. So we suggested to them, why don't you take a system from us? And this is how we now got a system at their place, and we call it the space quality plasma nitriding system. Second is the plasma assisted PVD coating that we have done for various space application. And one is the antennas, which are made up of Lexan. We developed a copper coating on it of 8 microns. And this was mainly to increase its reflectivity problem. Secondly, we also did this on bearings, where they required a coefficient of fraction of less than 1, and we delivered a coefficient of friction of 0.07. This was for improving the wear resistance. So more work on more coatings also will be delivered by Dr. Ramakrishna Rane. Apart from this, IPR itself ventured into applications for space on its own by the plasma physics knowledge they had with them. And then came the development of helicon plasma thrusters, plasma antennas, and cryogenic pumps. Plasma thruster activity started, and we are now in a way to develop a 90 millinewton thrust at the rate of 50 kilowatt. And in comparison to a Hall thruster, it has various advantages because it can move deep into deep mission, as well as there is no need of xenon. because we use a cheap argon gas. You can vary its impulse rates because of by using ICRH, that is ion cyclotron resonance heating, and with that you can have the thrusters that was mentioned earlier by Professor John Basamir, similar to that. Now these thrusters are electroless and no neutralizers are needed, and it can be easily scaled. So we are now working on the second phase as well as the third phase, and we will be doing it in some time phases. So for this, the participants over here from various agencies, we would like your cooperation for these problems, and Ms. Renu Bail will be talking more about this. The other work that we ventured into was plasma antenna. It is mostly for communication, and we found that plasma antenna is better compared to the normal metal antennas, because plasma acts like a medium which can be switched on and off. It can be used as a reconfigurable antenna, and it works as an auto frequency hunter. It can work on various bandwidths. So comparing to the monopole metal antenna, as you see in our radios as well as in our televisions, compared to that, it has various advantages over that, and its design is very simple and it works on low RCS. So these have found various applications in military as well as commercial applications. More about this will be dwelt by Dr. Rajesh Kumar. Cryogenic pumps is one of the most important pumps which are used for cryogenic applications in space by space organizations. An imported cryogenic pump works with helium, whereas we at IPR have come up with a substitute of this pump. We have built this cryogenic pump at a very low cost, and the first one is named as Agastya. And this pump is indigenously made. It works with liquid nitrogen, and there are no moving parts. So an MOA has been signed with SAC. We are able to make customized design as per the AVS standard pumping speed measurements. And more details about this particular activity on cryogenic pumps will be given by Dr. Ranjana Gangadre. Apart from space, IPR also has ventured into aerospace applications. And aerodynamics drag reduction is one of an important challenges that most of the vehicles face. So if we are able to reduce the drag, we would almost reduce the fuel consumption by 5%. And activities on this has been initiated in IPR. We have developed a subsonic wind tunnel for this, and consistent reduction in drag has been observed. This particular thing has been overcome by using a plasma actuator, which works using DBD, that is dielectric barrier discharge. And we have simulated it and have benchmarked with the earlier results. So we have used open foam CFD analysis, and you can see the results. The one above is without the plasma and one below is with the plasma. Simulated conditions, and Mr. Rajan Babu will tell you more details on this. IPR has a ICRS based 14 mega electron volt neutron ion radiation system, which has the following characteristics of having a neutron yield of 10⁻12 nanometers per second. It works in CW by pulse rate, and this particular neutron generator in this radiation facilities can be used for various applications like radiation hardness testing, radiation shielding of space equipments, and so on. Mr. Sudhir Wala will talk about this particular facility that we have in IPR. Apart from having physical models in IPR, IPR has very good scientists who also work on simulations, and CFD analysis have been used for space and aerospace applications. And we have used CFD plus 6 degree of freedom solvers to use for various applications. Some of these are like spinning flat plate and hypersonic flat plate. And we have also used them for deflagration to detonation transitions. It's a very good simulation tool that we have with us. And our colleague, Mr. Sandeep, will talk more about this. So today in the afternoon, when we move around for a tour, you will see most of these systems with us that are running. Apart from that, some of the technologies that Professor John mentioned, those also will be exhibited to you. So I request all the participants to please have a tour and look at the various facilities so that this will help you. Whenever you encounter a problem, you can always definitely come to us and we will be there to help you on. With this, I thank you for your patient hearing.
We can take 2 quick questions, please.
About plasma transfer in India.
Yes.
Are there any studies with respect to EMI, generative and plasma?
Plasma thrusters, renewable? Not yet.
Yes.
So yes, I have a question that most of the experiments and tech that we are building related to plasma are being done on on ground where there's a severe effect of gravity on plasma because in in the end it's a matter. So do we have any plan for creating microgravity based experiments in this domain of plasma which can be sent there and we can get the realistic effect of on plasma in space?
We do not have such facilities over here, but we will yeah.
Okay, thank you.
So let's thank the speaker once again. May I now request Dr. S. Nima to kindly present a memento to Dr. Alfonso. Thank you, sir. We have our next speaker, Mr. Krishna Mohan Shanbog from Liquid Propulsion Systems Center, ISRO. Mr. Shanbog is going to present a talk on plasma thruster for spacecraft, present and future. And I request him to kindly deliver the talk.
Good afternoon, respected former Chairman Kiran Kumar sir, former Chairman of DOE, and my Director IPR and all my friends here. Thank you very much for this opportunity. So our topic today will be the plasma thruster for spacecraft present and future. Broadly, first we will go through what others are doing and then what we are doing in ISRO. But when we talk about what others are doing, in plasma thrusters, various experiments, developments are going. But then how it is flying is very important. And what thrusters are flown today. So we will concentrate on those thrusters which is flown already today and maybe flying in near future. Because so when we talk about plasma thrusters, but then making thrusters is easy, but testing is very important because it gives very low thrust, but then we have to fire it for a long time to ensure that it is in a flyable condition. So, this is quickly, I'll go through what all the various requirement for the spacecraft propulsion system is well known. I'll just go through this: orbit raising, orbit correction, station acquisition. So this is not the topic, but just want to say that these are all the activities required for, it is required for the spacecraft propulsion systems. But then this slide, just I want to say that why the electric propulsion system is becoming important is that, see, if you use this chemical propulsion system, CPS, you see if you want to increase the delta V beyond some limit, it is not possible to lift these satellites because the launch most goes exponentially very high. So that is a reason probably electric propulsion system is one of the alternative for chemical propulsion. But then, of course, near planetary missions where we are using for say Chandrayaan or Mars mission, there we have to give the thrust in a very quick time. So that is not possible with the EPS systems. Of course, various energies used for the spacecraft propulsion system, this compressed gas, chemical, electrical, nuclear, and solar. In these slides, which I just want to say that how the idea of electric propulsion came into picture, you can see that, for example, in a chemical propulsion system, the thruster is basically the power plant. That weight is very less, but the energy source basically is the propellant. We have to carry a big amount of the propellant. Then the people came up with the idea is that this energy source can be reduced. So probably the nuclear and solar energy, the energy source, but then the power plant mass becomes high. So probably the optimization of this is very important when we talk about the success of this electric propulsion system. So of course, the solar energy, this is a typical propulsion system configuration. So solar energy, solar panel is always available in the spacecraft. So that we'll be using that. So that is means energy sources, anyway we should have it. So the additional energy source required for propulsion is very less, rather nil. But then we have small systems here, like a propellant storage tank and the gas systems and gimbal and thruster, and the power processing and control system, which converts the solar panel into the power to this thruster. So this total mass has to be optimized. So then what is the benefits of this electric propulsion system? Can say that, say all electric propulsion, the system came in the picture of full chemical propulsion system for a typical 4,800 or 5,000 kg of satellites, how the increase in the mass can be, the bus mass can be increased. So going for the electric propulsion system. Another important thing in here is that the xenon, whatever the propellant which we are handling, it's hazardless. So chemical propulsion, it's very hazard in nature. This is one of the major advantage which I personally feel now, because we are handling both chemical and the xenon. Xenon naturally, its handling is very easy, and in fact we call it as a ready to launch satellites. We can load the xenon and we can take to the launch pad. That is what's happening today. So what is this? Just I want to see some parameters which all of you know that thrust, ISP are the more important parameters for any propulsion system. Here only one thing we want to say that see, this is a thrust. If you see the efficiency of this thruster performance, kinetic energy divided by power given to the satellite. Finally, if you see that thrust and ISP, if a given power and efficiency of the system, then if you want to have more thrust, definitely IS will be less. It's a physics which we have to take into account. So this is the various types. Right now, we were working only on the electric propulsion system, the solar electric propulsion system, but then definitely, probably a nuclear electric propulsion system may be coming in near future, which we have to wait and see. This is the various types of the thrusters which is used: electrothermal thruster, static thruster, and electromagnetic thruster. Probably this is out of range now, because electrothermal thrusters, earlier Sir was also telling, basically converts the plasma into thermal energy and then evaporates. Then again, the material problems comes into picture in the electrothermal thrusters. Of course, electromagnetic thruster, an issue is that the magnetic field is basically used for acceleration of the thrusters. Then how to create this magnetic field is becoming issue. So probably this is very suitable if you want to have high thrust, probably high power is required here. That is why mostly electrostatic thrusters are very popular today in spacecraft propulsion systems. So these are various types of the thrusters we are using. You can see the various types are available today, but in spite of that, we have very, very electrostatic thrusters in this SPT or Hall effect thruster. Either Hall effect thruster or ion thrusters are very famous today, and this only probably we'll discuss further in our presentations. So Hall effect thruster, if you take, now you can see various types have come in, but earlier it was thruster with the magnetic lens, that HET with the ceramic anode chamber or a hybrid chamber. That means ceramic will be at the end of the thruster. Partly it is metallic thruster, that is hybrid thruster. This is where the ISRO has come in. We have started developing it. Of course, we are into this all ceramic chambers also. But then recently it has come, the magnetic shielded thrusters are the next version which has come in the Hall effect thrusters, which is right now very famous, and it is going to fly in near future only. Most of the thruster will be magnetic shielded thruster. Nested Hall effect thruster, lot of developments are going on, and other thrusters as suggested, as xenon is very costly, so krypton or the krypton plus xenon thrusters are used, but again it is used in the same design of the xenon thrusters. Otherwise, the aqua Hall, that's water Hall effect thrusters and iodine thrusters, some developments are going on here, but still it's not gone into the mission mode. So this is the just operation of the Hall effect thruster. Everybody knows most of the things. It has having an anode and a cathode. Basically, we are using a thermionic cathode, which emits the electron when and there is a potential applied between this anode and the cathode, and apply a radial magnetic field. So electrons are confined at the exit of the thrusters. So it becomes a virtual negative negative potential here. So once the xenon is ionized, it accelerates and gives the thrust. So this is the, if you see the history of the Hall effect thrusters, basically started by the Russians. So SPT 70 onwards, you can see here, Fakel is the only company which has developed, and most of the thrusters today flown are SPT 100 or SPT 140, mostly developed by the Fakel by Russians. And it was the SPT 230 also is developed, but not yet flown. But if you see the Keldich Research Center, which is also a Russian company, here also we had a good interaction with them. So we've flown this thruster in one of our satellites, but then they have developed other two thrusters also, which is having high power, slightly higher power. But then still 2016, most of these thrusters are not used for orbit tracing of the communication satellites. Most of the things are used for on-orbit applications. Once the satellite is into the geostationary orbit or wherever intended orbit, the control of the satellites further was used here. You can see here, most of the thrusters are Russian-make thrusters. This is in European satellites. So most of the thrusters are Russian-make thrusters. Of course, in we can see that some of the thrusters like PPS 1350G, though it is a European sat thruster, but they have taken the technology from Russia and they have developed this. But then all electric propulsion system is becoming after 2015 or 2015, these all EPS satellites have started gaining momentum here. So we have two satellites, which two thrusters, which is already flown and very popular, is the PPS 5000 and SPT 140. These are the thrusters which is used to take a satellite from geotransfer orbit to geostationary orbit, so that entire chemical propellant which is used, most of the chemical propellant is fully changed with the electric propulsion systems. So what is a magnetic shielded thruster? So this, till now we were talking about these thrusters, which is not like the life limiting factor was the anode liner liner. So what is this new technology which was coming to picture? It was accidentally found out during the long duration testing of a thruster called BPT 4000. In fact, what happened was that at around of 6,700 of firing of the thruster, this was modeled using a all 2D by NASA JPL people, and it was found that at the end of 6,700 hours, this was the type of the plasma which was coming out from the thruster exit. So you can see that basically how the ceramic was eroding is that high energy plasma was impinging on the anode liner. Basically, it is a ceramic liner and it was eroding. But at the end of 6,700 hours, the potential almost becoming equal, parallel to the ceramic liner, it was become almost equal. So it was the thruster erosion was almost became nil. So this is how the technology was found accidentally. But then they started designing the thruster for this requirement, and that is why this magnetic shielded thrusters already now designed by NASA, and these are some thrusters which is already developed by NASA. And then go back, I'll give just a brief on the gridded ion thruster, which is also very famous in US. They also used for and in all electric propulsion system also. But there the life limiting factor was not much was there like SPT. So these are the thrusters which was used in the by US for the all electric propulsion system. This was basically development of in US, this grid ion thruster was carried out. So in the low power section of the electric thrusters for Earth observation and scientific missions, this is another famous Hayabusa was the satellite from Japanese satellite, which was only 88 millinewton thrusters. So other small power thrusters are used for so many applications here. The latest one was that Earth observation satellite. So by Israeli fellows, this Israeli companies, Israeli Space Agency has used a satellite thruster, which is around 14 millinewton Hall effect thrusters for Earth observation point of view also. This is what I was talking about, magnetic shield. That means because of this magnetic shielding problem, the thruster life of these SPTs or Hall effect thrusters have now become very huge. Because of that, it is planned that as lunar Artemis 1 in the lunar gateway was planned by the NASA, wherein they are using a cluster of 12 kilowatt Hall effect thruster, which will be used to take a huge masses into the lunar gateway. So other alternative propellant, these are all the various alternate propellant which is used and tested, xenon, krypton. In fact, krypton thrusters are already used for a small satellites, which is used for Earth observation satellites, communication satellites by Starlink satellites. You must have heard Starlink satellites, Starlink satellites as well as OneWeb satellites. In OneWeb satellites, ion thrusters are used. In Starlink satellites, SPT is used with the krypton as gas because it is cheaper. Now in ISRO, we have done in small way the electric propulsion system in GSAT-9 spacecraft that is flown, and wherein we had, in fact, we were working for quite a long time. So it was a system which is used with the Hall effect thrusters of a very small power for around 500 kilo, 420 kilowatts. And this was used in GSAT-9 and this is operated for around 2,500 hours in GSAT-9 spacecraft. Each thrusters are operated for 650 hours. This thruster actually it was developed by Kaldish Research Center in collaboration with ISRO. And this is achieved thruster is slightly less because the power also it was less. But then next step is that we have to go for all electric propulsion system. So a study was carried out. What is the impact of that? So we found that around 2 ton of the 2 ton of the mass can be reduced using electric thrusters. So this is the type of the thruster which we are planning in next mission called Technology Development Thruster. So 300 millinewton SPT, stationary plasma thrusters, which is now qualified. I can say that it's qualified by our team. So this is the type of the power it will take. It's only a demonstration satellite wherein we'll demonstrate the thruster going from GTO to GSO using 3 thrusters with this, with all the requirements. So when we are developing a system, it is not that only development of the thruster, but then very important thing is that how various factors like this thruster vector should go to the CG of the spacecraft. So we are using a thruster mounting mechanism so that thruster vector is aligned to the CG of the spacecraft. So extensive tests are being carried out to qualify the flexible xenon feed systems we should have, then thermal management of the systems we should have, and more importantly, the power processing and control system which has to be developed. So these activities are going in full swing. So these are the thruster developed by ISRO. In fact, 75 millinewton SPT that is also qualified for space application. 300 millinewton SPT is qualified. 18 millinewton thruster is the first thruster we developed to start to know the thruster, how to operate that. But then we have made our own 80 millinewton thruster. In fact, we have developed one low power thruster also, which is around 10 millinewton, so that it is applicable for the constellation satellites around 200 watts. And this is fired for 200 hours in our facilities. Similarly, the magnetic shielded thruster of 300 millinewton SPT also is developed, but that's also work for 200 hours, and that's also in a qualification stage. So other low power thrusters which were developed by ISRO, which is not to the qualified to the space application, but still we have done some initial studies and a good development is carried out. It was the Teflon based plasma thrusters, around 50 watts, also a 5-watt thruster, both have been developed. Similarly, other research institutes like and startups, in fact, a microwave electrothermal thruster was developed using a startup with us. Similarly, a MPD thruster of low power with the Indian Institute of Science and with IIT Chennai, we have developed one small FEEP thruster, which will all take very low powers. So in conclusion, what we want to say is that with the development of magnetically shielded technology, Hall effect thrusters are gaining ground, are replacing the actually grid-ion thrusters for both commercial and scientific missions. And HET's developments are increasing both for Earth observation satellites as well as satellite constellations, both LEO and MEO constellations. Extensive research work is going on specifically because Xenon is quite costly. So how to replace this Xenon, and very difficult, costly, and very less amount of Xenon is there in the atmosphere. What all the other propellants which we can use? Already there was some suggestion, beautiful suggestion given by June sir. Similarly, electrospray, but in the small segment, still electrospray thrusters and pulse plasma thrusters are still dominating. Probably this is because it's a simple system. Specifically, pulse plasma thrusters are very simple system. So very less system mass. That's why it is very popular. Of course, grid-ion thruster and magnetohydrodynamic thrusters are possible. That is because it requires very high power. Probably a low power, it may not be that much efficiency. So this may be used in conjunction with the nuclear energy, which is possible for this spacecraft to come. Thank you.
The platform is now open for questions.
For the magnetic shielded thruster problem.
Yeah.
So is there an ongoing experiment at ISRO with your own developed thrusters?
Yes, we have developed a thruster and we have tested for 200 hours. And see how to say that. You can see that here. This is the normal thruster before testing. This is the thruster after testing. So qualitatively, we say that there is no erosion because what is black is nothing but when it is tested in a vacuum chamber, the sputtered material comes because we use a graphite liner in the vacuum chamber.
I understand.
So it comes and goes.
So the shielding part comes when you draw out the magnetic radial component outside the thruster wall, is it? That's what it is?
Yeah. So I think this you can see here because I'm not an expert in plasma, but still
I'm just asking about the magnetic field direction. That's all.
Yeah, it will be like this. You can see this is the magnetic field direction for this normal thruster will be like this.
Yeah.
Here it will be.
You're pulling it out.
Yeah.
Okay. All right. So that's my second question. You didn't comment about electrodeless thruster in ISRO program. Helicon thrusters and others.
Yeah, we are not into this research area.
There are no questions then.
Yeah. Anode liner material also changed. It's a change, but the basic design is coming from the original, the power versus the mid diameter. That is the basic design. See, basic design of a thruster size basically comes from the power of the thruster required. So mid diameter will design. Later on, it is changed for the requirement. Yeah.
Yes, one.
Yeah, I think this is where we want your support from the IPR. Basically, the plasma modeling and a small amount of modeling only was done, but that is not sufficient. In fact, our discussion with the chairman ISRO and all, that was the one requirement given was that how to model this proper model of the thruster performance parameters, how to model this. We are not up to that level. Probably IPR can really help us in this area. Already a small MOU was there, but that is not sufficient. It was a one-dimensional modeling was done earlier.
Sir, I'm interested in your 18 millinewton thruster. So basically, this life are 3000 hours. whether this has been tested continuously or, I mean, in parts, or what is the continuous?
See, what we today, how we are taking the life of the thrusters, what we are doing is we have a semi-empirical formula. What we do is that we fire the thruster for say 1,000 hours. We take the erosion rate at each interval, say 100 hours, 200 hours, or 500 hours. Then we have a mathematical model, then we'll extrapolate for higher life. For that purpose, we require what is the erosion happened in each after each time frame. That is a input which is going to the mathematical model. So based on that, up to 1,000 hours we fire. Then this mathematical model results are known to be better, which is 5 times better, up to 5,000 if I want a life. So minimum 1,000 hours we have to fire. This is one way of doing it. Another way of doing is what we do is we take this thruster and see the erosion profile, then extrapolate it and machine the ceramic to that level, then we can test. So these are the two approaches which is there to see the life of the satellites. That's what I'm telling. Every 100 hours we'll break. Yeah, we measure the erosion rate in the ceramic liner. Again, another like that. Erosions are basically initially, it is exponentially decreasing. Means initial erosion rates are very high. Later on, it keeps on reducing.
Yeah.
So in your initial slides, you made a comment about mission-ready thruster and thrusters which are sort of working but in the laboratory. So how do you qualify? It's sort of continuation of our question.
Yeah.
How do you qualify things to be mission-ready? Because I see there is a theoretical jump in the concept. Yeah.
Yeah, I agree. Because mission ready means what I mean to say is that, see, we can design a thruster, we can fire the thruster for small duration. But since as the thruster level is millinewton thruster, for example, if I want to fire to take GSO to GTO, a typical chemical propulsion thruster, which is giving 440 Newton, it requires around 10,000 seconds of firing. Now this is millinewton. So you imagine what is the level of testing required here. So mission readiness by firing the thruster for say 100 hours does not mean that the thruster is qualified for that. So it is one really challenge for any electric thruster designer to say that my thruster is qualified for this much hours. That is the point I want to say.
Thank you. So let's thank, yeah.
No, the answer to your question basically is, see what you are looking from this component, you have a functional requirement. Now, how to demonstrate that functional requirement is the challenge. See, what he was trying to tell is the total duration of operation of that is, let's say, 100,000 hours. Practically, we cannot do that long duration. So you have to come up with ways and means by which you can guarantee that what we have done will last for that. See, otherwise, after it is put, once it is in orbit, you cannot test it there. So mission ready is, how do we convince that what we are putting is capable of meeting the functional requirement? Some will be by design analysis, some will be by demonstration. And that demonstration plus analysis together is satisfying. See, obviously, we cannot be testing it for 100,000 at 1 million hours type of thing. So when he says mission ready, what he means is the mission management will be ready to accept this component as a entity in the system.
It's a combination of practical and extrapolation.
Yeah, extrapolation. Obviously, if you have a good theoretical thing and you can tell, like I talked about erosion. So now you are demonstrating by creating that eroded condition and test for a short duration, or accelerated life testing. That is what is required. So the challenge is in formulating that.
Thank you, sir. Thank you very much.
So let's thank the speaker once again. And so now I request Dr. S. Nima to kindly present the memento to Mr. Krishna Mohan Chandra. Thank you, sir. So Since we are running late from our schedule, therefore we have shifted the talk of Dr. Mukesh Ranjan to the second technical session. And now I request everyone to kindly proceed for the lunch. And there are few more announcements that we have arranged a visit to FCIPT laboratories from 2:15 p.m. onwards, whose coordinator is Dr. Vishal Jain. Therefore, I request all the interested participants to please gather at the seminar hall at 2:15 p.m. for the visit. And once again, I request all the participants of session 2 to kindly load their presentations during the lunch break. Thank you.
Hello, hello, hello.
Hello. Hello. Hello. आ रहा है? Hello. ठीक है.
Hello. 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 Hello.
Welcome back to the second technical session of PSAA. So here we have the first speaker is Dr. Mukesh Ranjan. And Dr. Mukesh is going to present a talk on plasma diagnostics and anode liner material erosion experiments for Hall effect plasma thrusters. And I request Dr. Ranjan to kindly deliver the talk.
Thank you, Amrin. Welcome to the second session of this today's seminar about plasma application for space and aerospace. We already have a very good overview given by Professor P.I. John and followed by Mr. Shanbok about the Hall effect thrusters. So we have a long association working with the different labs of ISRO, and we contributed for the materials development as well as the plasma diagnostics. So basically, my talk is summarizing the two aspects of the Hall effect plasma thruster. One is the plasma diagnostics, as well as the material erosion of Hall effect plasma thrusters. So before I start, I would like to acknowledge and our collaborator as well as my FCAPT colleagues. So we started this plasma diagnostics activity with LPSC Bangalore as well as LPSC Trivandrum in somewhere in the year 2005 to 2007. And Mr. Shanbok was one of the key collaborators from ISRO side, and Mr. Vijay Nandalan. So at that time, this activity was started in ISRO, and we helped them to develop the electrical probe, Langmuir probe, Faraday cup, as well as retarding potential analyzer. And with me, my colleague, Mr. Ramkrishna Rane, Kina Kalaria, Naresh Wagala, and Dr. Subrata Mukherjee contributed for this. And following this activity in the year 2012 to 15, we started working on the anode liner material erosion experiment. So thruster was already developed, and then the live testing experiment was going on. And then ISRO was in the development process for developing their own ceramic material. So they were getting ceramic from some abroad companies, as well as VSSC was developing their own ceramic material. So they wanted to know how good is their ceramic material in terms of the properties which is commercially available. So for them, we collaborated with Mr. Shibu Methu, Mr. Shanbok, and Mr. Vijayanandan again, and did a lot of customized experiment to match the quality of the ceramic material. So in this study also, many of my colleagues, because it was a very big MOU we did for the last 3 years, we did a lot of experiment for them. So many of my colleagues, they contributed for this. And then in the last recent MOU, what we have done that once the thruster is firing, slowly, some temperature is built up. So it can go as high as 600 degrees C. So once the temperature is rising, how the ceramic material property are changing. So those kind of experiment we have performed, and this MOU was recently finished last year. So with this, I will start my presentation. So basically, I have two parts. One is the plasma diagnostics, which is a smaller part of my talk. And the second part is the issue of plasma ion-induced erosion. These are some of the pictures which you have seen. So these are the retarding potential analyzer, Faraday cup, and the Langmuir probe, which we have supplied to LPSC. And this is a vacuum positioning system. So we wanted to characterize the plasma structure completely inside in situ. And so we provided the data acquisition system as well as the in vacuum positioning system, so that at multiple angle of incidence, you can align your probe and then do the plasma characterization. So what you see here in any kind of plasma ion source, people are mostly interested what is the ion energy, what is the plume divergence, as well as what is the flux. So you need to design very precisely your plasma diagnostics. But the key parameter is whatever is facing the beam will start eroding it. So if you need a plasma diagnostic, it has to be fast enough, and it has to be sustained at the energetic beam profile. So when we develop this plasma diagnostics, we face a lot of difficulty. Like many a times it happened that the motors and pumps which we have used for the vacuum positioning system, they stop working in the environment of plasma thruster because of a lot of contamination, a lot of heating effect they were started coming. So for them, we develop a plasma diagnostic system. So before I start, I will like to just give you a feeling what is plasma all about. So what you see in this animation, it's a very crude picture of plasma. So you have a slowly moving ions, pink color, and very fastly moving electrons. So what is plasma? Plasma is a weakly ionized form of a gas. So when you give some energy to the electrons which are moving in the surrounding of the orbit of an atom, so electrons comes out, and then what you have is the ions. So when a surface is coming in contact with plasma, what will happen? Because as I said, electrons are very fast as compared to ions. So electron will immediately leave to the surface, and what will remain on just in front of the surface are the low energy ions. So following the electrons, these ions will also move towards the surface, and then they will reach to the surface. And so this entire scenario can be divided in 3 categories. So one, the plasma will still remain charge neutral. So you will have electron as well as ions. There's a pre-sheath region, and very close to the surface, there is a sheath region. So inside the sheath region, what you can see, you have more number of ions because electrons are already lost as compared to electron density. And then there's a pre-sheath region where you still have a equal number of charged particle, electron as well as ion, but their density is lower than compared to the bulk plasma. So this is the typical scenario when any kind of plasma is interacting with any surface. Why I am showing you this animation is relevant to the plasma diagnostics. So the simple tool which is used to characterize the plasma is the Langmuir probe. So Langmuir probe is just a wire. So when it goes inside the plasma, you will have this kind of scenario. So the electron will immediately go to the surface of that probe, and then following the electrons, ions will go to the surface, and then they generate some current. So there are different kind of probes are available which can be utilized for different purpose. So one of the single one is single Langmuir probe. So you have a single wire. So this is a single Langmuir probe. You have 2 wire double Langmuir probe, and remember 3 Langmuir emissive probe. So single Langmuir probe, double Langmuir probe, they are used for measuring the plasma densities as well as the plasma temperature, electron temperature. So these are some of the properties which people are mostly interested when they are characterizing the plasma. But for the point of view of the thruster application, people are interested in plasma density as well as ion flux and ion energy distribution functions. So to calculate these 3 parameters, you need Langmuir probe, Faraday cup, as well as retarding potential analyzer. If you want to measure your plasma potential very precisely, then there is a probe which is known as the emissive probe. It basically emits the electrons to the plasma and then reach to the potential of plasma potential, and then it can give you very accurate measurement of the plasma potential. Then there is a MAC probe which talk about the ion drift velocities, and then Faraday cup, as I already told, is used for measuring the flux of the ions. So these are the this is the power supply which we have supplied to LPSC Bangalore as well as LPSC Trivandrum. And what is very special about this power supply? So let me tell you, so there are already international companies who are selling the Langmuir probe power supply. They are very, very expensive, but they are only using the Langmuir probe for giving you plasma density as well as plasma potential. But this, our unique power supply has 3 capabilities. So the same power supply can be used for the measurement of retarding potential analyzer. It can be used for the Faraday cup measurement. And so basically it has 3 parts: Langmuir probe, Faraday cup, as well as retarding potential analyzer. So ion energy measurement, plasma flux measurement, as well as plasma density measurement. So this kind of power supply along with the plasma diagnostic is a regular product of our division. We have supplied this kind of system to different industries as well as universities for different type of custom baked plasma diagnostics applications. So what this basically does, this power supply basically launches sinusoidal wave to your probe, or it can give a ramp probe. So in this, for example, minus 62 plus 40 volt. So in the same cycle, you can collect electron as well as the ions. So when the probe is negatively biased, it will collect the ions. When the probe is positively biased, it will collect the electron. So you are launching basically a sine wave to the plasma, and the potential which you are giving is non-perturbing to the plasma. So you basically so this power supply is giving this sinusoidal wave, and then you can collect the current from the probe, and then you can plot them. So this yellow color is the basically characteristic Langmuir probe characteristics. So once you have this information, you can find out, you can calculate many of the things about the plasma. So if those who are not interested to go deep into the physics part, so we have a software written. So you just need to collect your power supply, and the software will take care of everything. It will calculate the plasma density, plasma potential, plasma electron temperature, many things it can calculate. So this is how a typical Langmuir probe characteristic look like. So the potential is varying from 60 volt to minus 40 volt. This is the example. It's a very old data which I took in the plasma thruster lab at LPSC long ago. So you can see this region is known as the ion saturation region, and this is known as the electron retarding region. So based on this Langmuir probe characteristic, there are some equations which can be utilized for calculating the plasma density. And one simple thing which you can do without doing any calculation, simply when you insert your probe inside the plasma, the very first thing you can measure is the plasma potential, is the floating potential. So one can simply move the Langmuir probe from one location to another location, and then it can give you an indication how the plasma density is actually changing from one place to the another place. So you will have a special information about the plasma varying position from one position to the another position, which is crucial even for the thruster point of view. So all this measurement, let us say I did at 50 centimeter away from the plume. You can move your probe very close to the thruster and then see how the plasma is in the very surrounding of the plasma thruster. This is an example of a Faraday cup probe. So you can see normally all kind of ion sources, they have a Gaussian profile. That means the majority of the ion have certain energy, but the Taylor can have a slightly higher as well as slightly lower energy. But most of them, they follow the Gaussian distribution. So this is again the measurement I did for the case of plasma thruster at a 50 centimeter distance. And you can see it's not very much like a Gaussian, but it's like a Lorentzian, very sharp. So that means most of the anodes and the thruster, they're having the same ion energy as compared to the another typical ion sources. And the density was found to be 19 milliampere per centimeter square at a distance of 50 centimeter. So one can plan using the Faraday curve, one can plan his experiment to see how nicely the divergence of his plume. Like for the thruster requirement, the most of the flux should fall within 10%, within 10 degree of plus minus degree. It should not be deviate. That's why it is recommended by the ISRO application. So one can choose the Faraday cup to measure the plasma density at multiple angle of incidence and then see how well the thruster is designed. The third example is retarding potential analyzer. So what it does is basically it has a retarding potential grids inside. So this is a special design. You will see on the literature different kind of multiple grids are used for the retarding potential analyzer. So when the ions are entering from this side and you give a positive potential, so the ions having more than energy what you applied here, they will pass through this, otherwise they will go back. So slowly, if you plot different ion energy versus the collected current in this holder, you will see that it is falling. At one point of time, you will see that the most of the current is stopped by the potential you are giving here. So basically, you are screening the ion energy at different potential. So this is a very easy to fabricate and simple tool to which can tell you the ion energy distribution function. So based on this information, you can make a derivative of current versus the this voltage di by dB, and you can easily get the distribution of the ion energy in your system. So this also we characterize the indigenous plasma thruster as well as the thruster which was procured from Russia and did it for LPSC inside the LPSC lab. Another probe which is very useful, I believe, because all kind of ion sources now have magnetic field mapping. So basically, Hall probe is used for measuring the magnetic field, but the problem is it has a semiconductor chip which cannot sustain at a high temperature. So if you have to perform high temperature magnetic field measurement, you need a probe which can sustain at such a temperature. So my colleague Dr. Ravi, he developed this magnetic probes. Sorry, I think one picture is missing. So basically, it's a winding of wires, different windings of wires. I will show you how it works. So when the probe is moving very fast inside the plasma thruster and then comes back, because of the magnetic field induction, it gets the information about the magnetic field. So we did this experiment for LPSC by putting some heaters inside. So this is the movie where you can see. So this probe will go. So we have already mounted the heater. It is at the elevated temperature. And in the oscilloscope, you can see there's some signal is generated. So based on this information, one can actually find out the variation in the magnetic field. So what we did that at different temperatures, so we tune the by applying different heaters, we change the temperature inside the vacuum, and then we see how the magnetic field actually the peak of the magnetic field is shifting from peak value to the 180 Gauss at different temperature. So this probe is also very useful if somebody is interested to measure the magnetic field at an elevated temperature. So with this brief introduction about the kind of different plasma diagnostics we can use, even though these are the plasma diagnostics which are very easy to use, but in IPR we have many other capabilities, many different type of plasma diagnostic system which can be non-destructive. You can mount them in your systems outside and then get the plasma information, like what is the ionization state of the xenon ions, what are the impurities inside the plasma, or if you don't want to put any probe inside. So there are different kind of plasma diagnostics support we have available, or technologies we have available in our institute. So with this, I will now move to the main part of my talk, is the ion erosion experiments. So since morning, we have seen that SPT thruster, they are very commonly, or they have proven their technology that they can be used in the satellites. But what happened when the ions are hitting, coming out, they are ejected, slowly at the edge of the plasma thruster, they started eroding. And there's a relation between the angle of incidence and the sputtering yield of the material. So any material has this kind of dependency. So when the ions are falling at a different angle, there's a peaks coming out. That means at this angle of incidence, the material will erode much faster compared to this angle of incidence. So when the thruster is initially developed, it is very smooth. The roughness is also very low. But slowly at the edge, it started eroding, and then the angle of incidence is no longer now parallel. It has some angle dependency here, and locally I will show you later on. So this angle is changing drastically. So at the edge of the plasma thruster, there is a possibility that material can erode much faster as compared to the its initial condition. So these are some of the pictures which I have taken from the literature, and I think the LPSC people might have seen in their lab also. So these are the places where the ions are hitting, and then initially it was very smooth, and then you can see these are the trench which are created by the ion bombardment on both sides. So basically, the ceramic material is removed from this place, and then it can now, after removal, it can redeposit some certain other places. And once it is eroding after several hours, there is a possibility that finally the magnetic yoke will also visible. So it's a serious issue which has to be avoided. So I introduce you that this kind of plasma erosion can lead to many kind of problem. So whatever the material is eroded from thruster, it can also deposit it on the solar panel. Even if the few monolayer of ceramic materials are deposited on the solar panel, it can degrade its efficiency. And it can also lead to arcing, because it's a different material which deposited on the surface. And if we see nearby some potential, some arc initiation is also possible. And reduction in thrust efficiency is also possible. And it's a failure of 80% of the thruster. This information I got from the literature. So we have to see how to avoid the material erosion from the edges of this thruster. And mean free path inside the vacuum of the eroded material is very high. So it can go from in the space, it can go any far. So to study this experiment, we designed a very specialized facility and in collaboration with LPSC and VSSC. So basically in this facility, we're supposed to do experiment starting from 50 electron volt to 500 electron volt. And we choose the same flux which are there in the thruster facility. And angle of incidence was chosen from 0 to 85 degree. And two type of information was required to be measured. One is the total sputtering yield. So what is total sputtering yield? When an ion is hitting the surface, how many number of the metal is eroded from the surfaces? That is the information about the total sputtering yield. Another is differential sputtering yield. That means in what direction, how much amount of the total sputtering yield is going in different direction. This information is much more crucial as compared to the total sputtering yield, because it not only tells the trajectory of the material, which is in which direction it is going. If, for example, the thruster is totally unstable, so material can go and deposit on the solar panel. As I said in the beginning, that ideally the plume should be remain within 20 plus minus 10 degree. But who knows, in a certain scenario, the material can erode even wider angle, and then it can go to the solar panel also. So that's why getting this information of differential sputtering yield is important. So for this, to perform this kind of experiment, we designed a special facility where we have an ion source, we have a specimen, and then we use a quartz crystal microbalance. And this facility can rotate the quartz crystal microbalance at multiple angle of incidence, so that it can capture the material in different direction with respect to the ion beam and with respect to the surface normal of the sample specimen. So you can capture material here, you can capture material here, you can capture in different direction. And then in this facility, we can also rotate the sample holders to make the scenario of multiple angle of incidence. So what you see here is the angle of incidence is now changed. And then again, we rotate the angle of incidence of the QCM. So QCM is typically used in thin film industries for measuring the thin film rate of deposition. But in this case, we use a special sputtering QCM sensor The specialty of this QCM sensor is it do not allow to interrupt the electrons, because in thruster environment or in ion source environment, you will also have electrons which are coming from different sources. So it has a specialized magnetic field which do not allow to disturb the data of the QCM, because the measurement I'm talking about is the nanogram per second. So a very, very low erosion rate we have to measure. So we do not want any kind of noise in our signal. So initially, a lot of experiment we did to calibrate our QCM as compared to for the standard samples like silicon, like different kind of metals, so that we are sure that the QCM is measuring the correct sputtering yield, which is reported in the literature, before we moved on to the sputtering yield measurement for the boron nitride silicate. So this is the schematic diagram of the same system I was talking about. So this is the ion source. So ion energy in this, we have a capability to go from 100 electron volt to 2000 electron volt. And from here, we can mount our specimen. You can rotate it at multiple angle of incidence. And this is the quartz crystal microbalance. So this quartz crystal microbalance can go at multiple angle of incidence, as shown in the previous animation. So what you see in this, based on this QCM measurement, I show you two plots. So in one plot, when you see then the 500 electron volt ions are bombarding at a normal incidence, the profile is isotropic. And when it is falling at a 70 degree, you see, and in one direction, we get much more material eroded as compared to the another direction. That means initially the whatever material is eroded, it is going isotropically in all the direction. But slowly, if you have a angle is changing, it can go much faster in one direction as compared to the another direction. So like this, we did a lot of experiment at different angle of incidence, different ion energies, 100 dB, 300 dB, 400 dB, 500 dB, and plotted different profile of what you see here, and then see how this volumetric sputtering yield of the metal is changing under different scenario. And then we wrote a MATLAB-based program which can actually, based on the information you have collected using the quartz crystal microbalance, you can put that information, and then there are some theoretical understanding how to calculate based on the QCM information, how you can calculate the total sputtering yield of the material. We wrote this this computer program. So one has to just simply upload the data file, and then simply by putting your experimental parameter, one can simply calculate the total sputtering yield of the ceramic material. So finally, our experiment did a lot of good information. So because these studies were planned for 17 millimeter thruster. So what you can see, we compared two types of material. One is boron nitride and one is boron nitride silicate. So what was the observation? That boron nitride silicate has slightly higher sputtering yield compared to the boron nitride. And around 55 degrees, there is a jump in the sputtering yield of the material. And because it was planned to operate around 500 electron volt, and our experiment was suggested that somewhere near 450, there is a jump in the sputtering yield. So it was recommended that at that time, what was the material developed, we should not cross this ion energy. Otherwise, there is a possibility that it will erode much faster. So these were some of the findings which were very useful for the VSSC. So based on this information, VSSC started developing their own material, and then every time they send us their specimen, and when we do the same experiment and give them the feedback. They also wanted to know what is the threshold of ion energy where the metal started eroding. So we did some simulation for them, and then found out somewhere around 70 electron volt, the boron and nitride started eroding. So because ion source cannot sustain whatever facility we have, it is very much stable up to 100 electron volt. If you go down, the beam is very much diverging. So we did some extrapolation and some simulation to give this information. And what is very obvious that as you increase the ion energy, the sputtering yield increases almost exponentially. So if you are going more and more higher energy plasma thruster, there is a possibility that there is a shoot up in the sputtering yield. So, and then finally, in the very recent MOU, as I said, so we did experiment for elevated temperature. So we developed a specialized heater which are UHV compatible and can sustain in the ion beam condition. So we changed the temperature from up to 600 degrees C, and then we found that there is a linear increase in the sputtering yield of the material. These are two type of at the two different angle of incidence. And so this information was also very crucial to develop the material. So finally, we get different kind of specimen from VSSC and develop under different condition, and then successfully develop this boron nitride silicon material, which has actually 20% less erosion as compared to the commercially available ceramic material. So it was a very successful completion of the work. What's something very interesting, what we have seen in our experiment, that Normally, if you see any literature about boron nitride erosion, you will see they are always reporting some micron sign images. So if you zoom and see high resolution images, you see there are some at some terraces, this kind of pattern forms on the surfaces. This is an indication that the local angle of ion bombardment is not same at all the position. So somewhere you can see the surface is very smooth, and somewhere you can see this kind of pattern formation. So we assume that when we that the ion incidence is 60 degree, but locally it may not be 60 degree, it can be 40 degree, it can be 5, because you have different grains of the material which can locally change the angle of incidence. So we did some, we generated some understanding why this kind of pattern are actually formed and how can be avoided to make this kind of pattern formation. So we did some simulation, and then already there's a theory which talks about that if you have a different roughnesses at different places, the ion bombardment at the valley is compared to the hill is different. Material eroded much faster in the valleys as compared to a hill, which makes the surface unstable. And that kind of irregular sputtering yield at different location can actually make this kind of pattern formation. So we did simulation for this study also. So finally, it was a very successful MOU, and there was a technology transfer meeting was arranged by VSSC to hand over this developed material to LPSC, and IPR was the part of it. So we feel very happy to be part of this study. And the meeting was chaired by the current chairman of ISRO, Shri Somnath sir. So with this, I would like to conclude my talk. So what we can offer to the different delegates sitting here. We can do different types of customized plasma diagnostic system. We can develop a specific plasma experiment if needed. We can also help for plasma metal interaction experiment using developed ion beam facility and surface characterization. I already have interaction with some of you who are interested in this kind of work. And so there are a lot of possibilities. We have a theory group who can develop the codes for the plasma thruster. We have different other kind of plasma diagnostic system which are used in tokamak, but of course they can also be used for the study of plasma thruster. So with this, thank you very much for your attention.
The platform is now open for some questions.
Yes, sir. I use Xenon only, sir.
Second. On the sputtered pattern, there is an azimuthal structure, modulation. Right?
Yes, sir.
Azimuthal.
Yeah.
So what is the reason for that?
I quickly actually explain. So what this theory talks about, it has basically it's the Bradley-Harper theory. It has two terms. One is surface diffusion as well as the surface erosion term. So because of the temperature, because when the ions are hitting the atoms, they release some energies to these atoms. So they try to go into the equilibrium. So like somebody is digging something and somebody is trying to put it at different places. So this surface diffusion and surface erosion, they are fighting each other, and then because of that they are landing in this self-organized pattern formation in the surface.
Okay, if I say that the plume has an azimuthal structure, is that a possibility?
Plume has an azimuthal structure. Even
because it's passing through a magnetic field, it can drive instabilities in the plume. So it forms a azimuthal pattern.
Because of that, it can have some local angle changing. That is the possibility. That's what I was telling. So initially we assumed that in my experiment angle is 60 degree, but it may not be 60 degree. Locally it can be changed because of the azimuthal or some other effects. No. See, the time scale in the ion, when the ions are falling on the surface, it's totally different. So one ion to another ion, there is no linking. Under this flux condition, what I was telling about. So every ion has some impact on the surface. So it makes some collision cascade on the surface. So in the time scale, when the surface is trying to relax itself, another ion is coming. So that combination of the way ions are falling on the surface makes these patterns.
Okay, I think.
Yes, sir.
I think to a certain extent is right, because what is happening, we have a breathing mode oscillations, which is 25 kilohertz. Along with that, azimuthally you have some. Probably that may be creating the issue.
Yeah,
Okay.
direction. Yeah.
Okay. That next question, my thing is that you have talked about everything in the. Do you have any non-intrusive type of plasma diagnostic system which you have? Probably because why we are asking is that, see the opening the chamber,
and putting this
Yeah, I have not.
specifically because
Yeah,
this diagnostic
I got your
systems.
point. I have not included in my presentation, but as I said, we in IPR we have microwave interferometer, optical emission spectroscopy. There are many other diagnostics available in IPR, and actually we offered them in past but somehow it was not. Decided, but we do have many characterization which you don't have to disturb your plasma thruster, or you don't have to mount it inside the system. You can simply mount it on the viewport and then get the information.
Okay.
Yeah. Thank you.
What is the surface because of the
Okay. So ideally speaking, there is no perfect surface available. You always have some atomic roughness. Even if you buy a perfect single crystal silicon wafer from the market, it will have some atomic terraces as well as hills and valleys. So even if you have one atomic level of roughness on your surface, you will end up this kind of pattern formation because this will generate this scenario of hill and valley. Okay, so this kind of pattern formation is most likely happening to be there, even if you have a perfect flat surface in your definition. Yeah, so if you increase your fluence, so this experiment, for example, I did for a short duration. If you keep on doing, there will be a possibility once the equilibrium of the surface is achieved, because what I believe that because of the different angle of the grains inside this boronite material, this scenario is created. If after several erosion of removal of the surface layers, maybe you will have a flat surface again. Possible. This kind of long hours experiment we have planned in future now. This I did, for example, I did it only for 1 hour experiment. Thank you. Yeah. It's time bearing. Yeah. It will achieve, for example, this wavy nature is also expanding. Temperature is contributing, ion energy is contributing, but at certain long hours of operation, it will become stable, then it will not change.
If we use this place for a long time, then it's not happening, but
in simulation also, it's very, you need very high computer facility to run it for a long hours. The window you see here is hardly 50 nanometer by 50 nanometer.
So now let's thank the speaker once again. And may I now request Dr. Alfonso Joseph to kindly present a memento to Dr. Mukesh Ranjan. So we have the next speaker, Dr. Vinod Kumar from InSpace, who is going to deliver a talk on space sector reforms in India. May I now request Dr. Vinod Kumar to kindly deliver the talk.
Yeah, very good evening all. I should first thank Director IPRC and management of this workshop or conference for inviting me on such a vibrant topic of the year, that is space sector reforms in India. We had very nice talk from Professor John in the morning, plasma, and we are seeing the real application of plasma which is affecting the human life as well as the space sector in that. So this is a very different topic. Generally, to give a technical talk, now it's totally different. So this whole story started in 2019, where present government led by Prime Minister Modi carried out it's not moving, space sector reforms in India. 2019, they formed NSIL. So, how many of you know what is in space? Very less. NSIL. Okay, what is the difference? All these things, probably certain things I will do. And what is the mandate of in space and NSIL? You say this is ISRO at the center of Department of Space, which has around 15, 16 centers specialized in all aspects of space. We call all three verticals, that is upstream, downstream, and midstream. So all technology we have here. The government of India has a vision to use these technologies and make it available to the common man also. ISRO was doing a very fantastic job, and they have developed all this huge infrastructure India has. When we discuss with some foreigners, they really say, yeah, India is amazing country. When last 1.5 months, over 25-30 meeting I had from various countries, and it's really amazing. So in 2019, government made New Space India Limited, that is central public sector enterprises like Antariksh. Now, this is the commercial arm which will which can commercialize the products of ISRO to the world or wherever you want. Now, Department of Space, which reports to Prime Minister and aided by Space Commission, has autonomous bodies as well, which is PRL Ahmedabad, NARL Gadanki, Northeast Tech, Semiconductor Laboratory, IIST. These two are educational institutes, basically, and IIRS also should be there somewhere in this. And then came the InSpace on 24th June 2020. The Indian National Space Promotion and Authorization Center was formed as a continuous. Purpose of this was to enable to open the space for all. Earlier, space was restrictive design. Only the few can work, others were working as a vendor. Now, with the opening of this, any person of Indian origin can work for space in any vertical. They can work in launch vehicle, they can manufacture their satellites, they can work on space data products, they can orbital slots and all that. So this is started, and here we go. The InSpace organization structure is like this, where ISRO and DOS advises the chairman in space. Space Commission also advises, and we have a board headed by a chairman in space, Pawan Kumar Goenka, and then we have 3 directorate and 1 joint secretary to take care of legal, finance, and other matters. We have a promotion directorate which is headed by me. My colleague Dr. Jain is heading the program management and authorization directorate, and technical directorate is headed by Mr. Rajiv Jyoti. So this is the structure, and our team is placed around 30 people have joined till now in various capacities, including the IAS, the Municipal Commissioner of Ahmedabad has joined us recently. So India's space journey. This is a very touching slide, how we started in 1963, and this is this year launch in 2022 where 36 satellite by GSLV Mark III was. So this is the way, the humble way which we developed over the year, and now GSLV Mark III is the Mako, and it is well recognized all over the world. So this is the time where government has enabled the private people, non-government entities through InSpace. This we had recently, you might know, 18th of November, the sky route has successfully gone up to around 90 kilometers and demonstrated the first maiden flight of a private launch in India. And I think some very few countries over worldwide may have this capability. So now government main aim is to act as an enabler. So what all government can do is through reforms and enable it so that the people can work. Yes, these reforms, we were given these 4 verticals that about which in space evolves. That is, first is the promote in space. So various activities are carried out in this, like student space force, generation of space force for future space force. We have international relation, industry outreach, various kind of verticals has been given in this. Then enabler, to enable, because space was a restricted region, as I have told you, and now it is open for all. So people may not know. So that's the another thing, how we can enable them, how we can help to take up the space activities, and if you have already taken, how we can help them. Authorization is a normal process to act as an authorizer to carry out the space activity, and supervisor. So you have to handhold the industry, you have to guide them, you have to provide with technologies available, whether you need some facilities, all these things, all these 4 verticals of in space, we have integrated nicely in a digital platform, which I will describe in subsequent slides. So, so these are the certain activities with international outreach. How do we carry out the startup enable? The very interesting part is this: the foreigners are coming to us. So our job is to promote, make India as a manufacturing hub in space, make for others. So that is the mandate given, and we can see the mutual benefit technology, how to it can benefit the Indian space sector. In startup enablers, as I have told, that they want to use facilities. The very interesting thing is they may not have the expert with them. So they don't have to do anything, they have to write to us. That too through a digital platform. We have an expert database. We have the 400 plus experts available in our, we will search from that, and we help them. Okay, this person you can contact and he will help you. So these are the certain kind of things which are as an enabler. And you see what are the verticals India is working. This supported by ISRO. The biggest support is the infrastructure. We have the facilities. We can request ISRO to use their, any private person can use those facilities, expert and other to carry out the space activities. And we are just championing that. What are the things we have? You know, PSLV, GSLV Mark III, and SSLV is coming. And we are transferring this technology to industry shortly. Space segment, we are in communication, navigation, earth observation, space science, you name the segment, we are there. We have a unique navigation system. And we make the satellite from nano to 6,000 kg, like GSAT-11, the giant. Space application, space data product and services. And we have a Google of Map My India. They have app also that works very nice. How many of you use that iMap, that Map My India app? I use anyway. It will not leave you in jungle like Google sometimes does. Just try to use that app. That is that one. I asked him, why should I use your app? He told it will not leave you. It will give you correct thing within 10-meter precision. In Bangalore also, many times I was left around a park. I was not able to find the place. So he told me I was very happy and installed that. So space, we work in all these 3 verticals: blue economy, green economy, digital economy. Digital economy, all of you know that we are the #1 in the world. As morning sir was telling that we have a very good space for that force. The technical know-how is with us. So the government of India slogan is minimum government, maximum governance. Really, it has helped from space. They have caught the tax defaulters, you know, from using space technology. What are the verticals here? You can carry out crop insurance, crop intensification, soil health card, urban regeneration, to name few, watershed management. I'll tell you how tax evaders were caught. Some gentlemen were keeping, they have farmhouse and there no crop is, they were claiming a lot of use. So they took some 3-4 year picture from ISRO पकड़ लिया उनको. So these are the kind of things space can do, and you see that now when you don't ask anyone, I have to go. You will go to Google and okay, this is the place. So this is what space technology we need. Now see, cities are saturated. You can use, or government can use this technology to decongest the cities. Other day, we were having some discussion with the Science and Technology Minister. We were telling him, sir, this is possible with this space. How you monitor the morning data of the office goer, see which side traffic is coming, where jams are experienced. You do something for that. You will have the real-time data. That's what we are expecting the space policy, which we have already submitted, and FDI policy. It can come anytime. So when it comes, more clarity will emerge. And yes, we are doing still as per the existing norms. We are enabling the private sector. You see, these are the kind of certain things, and it helps. Some of people were telling the mining people are using the GPS, our Navig technology. They can track their truck movements. Earlier, what you used to say, okay, 10 trucks he will take there and 2 trucks he will transfer. So it's saving. So it's the space technology which is helping people's life and reducing corruption. Digital economy, I need not say that 88.4 billion payments in 2021. Big number. You see, today, earlier I used to see that when digital, that UPI was made, people were laughing. I have seen the big people laughing. But today you see, anyone is doing is the digital transaction. How it is possible? It's all space technology. ATMs you see, WeChat terminal. Now, Government of India has carried out the satellite reforms this year, 2022, wherein a lot of charges are waived off. You can see the report by Department of Telecommunication, where they say that 21 lakh per annum was for NOCC, Network Operation Control Center. Then after that, 10,000 per network, they used to all waived off. So it is the just government is enabling you to do business, to come into the market, do your. Now it's a very interesting technology. In remote areas, you may not have the internet. We have GSAT 11 with the spot beams. I think 10 megahertz is taken by Hughes. So they have a very small, like this box. They can go put it in Himalayas anywhere up to 1 kilometer, 2 kilometer. You can enable the satellite-based internet. These are the kind of things which are happening. And you see that this year, July, 284 billion digital transactions. Are we less than anyone? We have saw it in COVID time by developing 3 vaccine. No, none of the top economy could do it. We could. We are the world leader in digital transaction. Why we should remain behind in space? So I see very interesting data. I will show you wherein you will see that yes, our youth can do it, and they are on the job. So you see the blue economy, very interesting study here. So you see, this is the work of 3 ministries those that has come together to develop a life-touching application, where the government says that it should benefit the common man. Antodaya we call it. So that's the way morning Kiran sir was telling about this, the potential fishing zones. This is the best example wherein a common man is told that, yeah, you can find the fish there. It is the space technology. It tells that this is the place. Not only this, they have integrated the low Earth orbit data with the Navig data, wherein he can go there in case of any distress alarm. He has to just press a button. The rescue team will reach there. This is the kind of thing we have. Then why we should be left behind others? Why should not be the leader in this space also? You see how this blue economy works from space, where he is given that this is the potential fishing catch that you can go through satellite. It will see the data is real-time process. Scientists will tell this is the chlorophyll here, and you will find the catch here, and the corrections are also applied there. So these are the some of the examples which I thought I will share with you. Otherwise, each topic is big that half an hour is not sufficient, right? So now, as a mandate given to InSpace, we came out with a very nice idea that we will do it paperless. That was our. So in April we joined, and by August 16, one InSpace digital platform, you can visit at this place, and you can register your company, you can register your association, you can put questions to us, you can ask questions, you can put your requirement online, what you want expert advice, you want technology transfer. First we will ask your capability, and you want to use some facilities, you want to launch the vehicle, give your requirement. We will assign the team automatically, and your problem will be solved. And it is being developed as a single window platform, wherein all agencies, it is our duty to connect you to them. You may need help from Department of Telecommunication, which WPC is the wireless planning cell, which controls the wireless allocation of this thing through ITU and all. We will connect. You need the ministry, other ministry, DPIIT or other. We are there to help you. So these are the kind of thing which government of India has envisaged, and we have put it on this platform. It's a very nice platform. For that, if you can, please, can you go to this website? Before I go to, can you just click this website? Is there? Internet, I think, is there or no? Well, later we can see. So, I mean to say that government of India has done its job. Now it's up to the youth to carry it forward. So then only, and I will tell you some of the statistics. Other day, Department of Telecommunications telling 893 transponders. You know how many of these transponders are our by ISRO? ISRO cannot do that. Around 360 or so. Rest all are fodder. Why can't our own Indians can do it? It will create jobs. It will create all. So this is our this thing website, wherein if you go, you log in here, you register here, the login here. It will ask certain questions. Just go to dashboard. Yeah, just somebody of. So we are very transparent. Whatever is coming to us, we are putting here. Till now, 155 proposals has come, and under various category what they have come, and how many NGs, other things are registered with us: academia, government, industry, micro, small business. Come down. So 307. This was started on 16th of August. So there is a juice, there is a potential in India, and proposals also 155 proposals we have. So, so it means there is a wave in the country, and various people are asking under promotion category also. Please give us this, give us that. Go back. It's okay. So you can just see. Please go through, and whatever we can do possible, certainly we will be doing. You can close this, please. Yeah, next. So this was envisaged in spite of all kind of bureaucratic hurdles. We did it in a record time because you know, approval process, when over a crore or around 2 crore project in government you are implementing at such a fast pace, it has its own troubles. But yes, government is with us. Next. Yeah, this is a kind of spread which I have that ecosystem which is making. So all the people are registering, and we are sending such information to Prime Minister office. They are asking us repeatedly that kya chal raha hai in space, how the ecosystem making. Next. That's all. Jai Hind. If you have any question, I will take it. on our website through some approval processes there. But from that database, we will connect you to the expert. See, we will connect you. After that, it is you have to talk to him and discuss with them. That we will not come into between. No, zero charge. No charge. We don't charge any fee. We will connect you to the expert. It is between you and expert. How you pay him, how many hours you work, what is your, it is left to you. Yes, sir. Now I'll ask director, sir. You are asking any question. Anything is there, sir. If it is.
My question is too big to be answered here. It's about the basic structure of InSpace.
Yeah.
How is it organized?
That.
I mean, this is the structure is fine.
Yeah.
It's about when you suppose you allow a private sector partner to make use of ISRO facilities. What happens?
See, first thing, private sector will come register with us. He will put his proposal online. We will give him, this is your request number, and we will assign one deputy director or assistant expert in that to interact with him. He or she will understand the requirement of that NG, whoever has applied. That NG will decide, okay, he wants this satellite testing facility. Now we have worked out SOP with Department of Space, where we and that center will have, and that NG tri-party agreement will be there. That will be NDA and non-disclosure agreement, and MOU will be signed by all three to execute that. He should not go and take this technology gift. So that covers all this ambit, and he start doing work there.
And have you standardized those agreements?
Yeah, we have standard MOUs and NDA also, but for foreign we are trying to make it, because for Indian thing it is done, but in foreign some country will say, I want it should be jurisdiction of his country. We want it should be neutral country. So all these things are going on.
Do you also include joint projects that have been projected between the ISRO lab and the private partner or anybody else?
See, here one catch is there, very right question. See, we are here to enable private. If private wants to come, he will. ISRO can do as it is. They can go directly to any private, any college, any industry. So ISRO doesn't need, government doesn't need permission from government.
The private partner.
Yeah.
And you have connected with the ISRO lab.
Yeah.
You also arrange for the
Periodic reviews.
The IT sharing agreement, the agreements.
Yeah.
MOU or whatever.
MOU, NDA, we share with them, and we are a tri-party to sign with ISRO. Yes, sir.
And then if the property is taken, you also have holder of that.
No, IP is the generally what is our rule. Now we are working out other things also like seed fund scheme. IP we don't claim. IP should be with the person who has developed. But generally now presently we are getting proposals to use the facility. So IP doesn't come generally. Yeah.
Any question?
To mention, we have designed a very specific space technology minor, and this is under approval process of IIT Bombay and IIT Madras. I am expecting this should start in January this year with the introduction to space technology. Now what we plan is when this is implemented there, and the chairman UGC and AICT wants it to be implemented across the India. So this is the one which has all launch vehicle, satellite, and space data product and services. We have made it, and one unique course which is optional in this, that space economy, space tourism, space law. For that also one optional course we have made. So like this one, there are the 4 major courses. One prerequisite is there. In addition to this, academics are asking us to, some of the NGOs and some of the people wants to develop syllabus. So for that, we are connecting him to the expert who will handhold them and guide them. Even what we do is not necessary that if expertise available outside of ISRO also we are trying. Let's say lab facilities here. our database contains the expertise capability of industry also. Out of this 300 plus, we have 175 plus industry also. This industry database also we are validating, and let's say some small test is there. Okay, we'll say fine, you try to explore with him rather than disturbing ISRO. So such things also we are going to build. Yes. With academia, one more thing which we are working on is the incubation center. All over India, we have a plan to open incubation centers with some of the IITs or academic institutions, where private company can go to that incubation center and do their research and this thing. So that plan is also under approval process, and we can see next year many systems. Yeah.
If there are no more questions, then let's thank the speaker once again. And I request Dr. Alfonso Joseph to kindly present a memento to everyone. So we have our next speaker, Dr. Suryakant Gupta from IPR. And Dr. Gupta is going to present a talk on spacecraft plasma interaction experiment and in the indigenously developed ISO test facility for the ESD detection on satellite solar panels. And I request him to kindly deliver the talk.
So thank you very much. As you have seen during the visit, that we have a ISO test facility for the validation of satellite solar panel. So the name of this facility is Spacecraft Plasma Interaction Experiment SPIX facility. This is a collaborative project with URSC ISRO and our IPR center. So as you all know that there are three major components in a satellite: antenna, transponders, and solar cell. So this talk is primarily focused on the segment that is solar array, this part of the satellite. Unfortunately, this was a animation, but PPT file is not working. So now it's in PDF, so you cannot see that animation. But briefly, I can tell that typically the bus voltage in any satellite is kept 42 volt. But as you know, the power rating requirement is increasing because the addition of new functions in the satellite. We need the high power satellite. So when we go for the high power satellite, there is a need to increase the bus voltage. So when we increase the bus voltage, then this type of arcing takes place, and these arcings are very dangerous for the satellite because it can cause the false communication signal. It can damage the electronic onboard circuitry like sensors and other things, and it can also damage the solar cells. So this is a very common slide which is being used among the spacecraft charging community, and you can see the insurance payment is dominated by the solar array failure because 49% of the solar array failures cause the load or burden on the insurance companies. So nowadays, it is becoming mandatory that the solar panel design should be tested or validated through ISO guidelines, ISO 11221. This is a slide. Actually, it was animated. So by this slide, I am trying to explain you that what happens whenever this energetic electrons bombard on the satellite solar panel. So solar panel is basically made out of glass, that is the cover glass. It is an insulator. Then the interconnect, that is metal. Now what happens whenever the charged particles falls on the solar panel, then the whole panel gets charged to negative voltage, which is shown by the black curve. Say, for example, you can see it is a minus 5 kV. Now what happens, because this is a dielectric material, glass, so secondary electron takes place and it becomes less negative. So an inverted potential gradient arise on this surface, and this causes the arcing on the solar panel. This is one of the conditions. There are several conditions for the arcing, but this is one of the conditions. And after the arcing, again the potential get normalized. So this is the basic phenomena of arcing in particular case. So the arcing can be classified in this primarily 4 major categories. So this categorization is based upon the ISO document, ISO 11221. So this document has been prepared by NASA, JAXA, ESA, and a few other space industries people. Fortunately, I have also contributed in the initial days of this formulation of this document. And here you can see, as per the ISO guideline, the whole network can be divided into this way. Like this part resembles the solar panel circuitry of the satellite, and the right part shows the load, that is the payload part. So now what happens when we expose this solar panels to the in this circuit, then we get the arcing. Those are very similar to the arcing happening in the space conditions. So in order to address this problem, IPR from Department of Atomic Energy and URSC from Department of Space, they have started a collaborative activity. It is named as a SPIX. So the URSC is located in the Bangalore, and we are located at Gandhinagar in the same campus. So under the SPIX activity, we had two targets. First was the plasma studies. Under the plasma studies, we were supposed to develop a LEO-like space environment in the chamber. And for the irradiation studies, we have developed a electron gun facility by which we can simulate very much space-like geo condition in the laboratory. So when I say LEO and GEO, so these parameters you know, but basically it depends upon the particle energy and the particle density in the chamber. So for LEO, the energy is of the order of less than eV, and the density is 10⁶ cubic centimeter. Whereas in case of GEO, the energy is of the order of few kV, and the density is very less. So this is a complete schematic diagram. As you have seen during your visit, this is a big chamber in which we create the LEO and GEO-like conditions. So to create GEO-like conditions, we are using a electron gun. This electron gun basically shower a flood beam on the solar panel. And to create LEO-like conditions, we have a plasma source just behind this circuit. So this facility already you have seen during this today's tour. So this is the electron gun, and just this is the plasma source, and this is the camera. So basically what happens whenever there is a arcing, so we get two type of signal. One is the electrical signal, which confirms there was an arc, and some optical signals which we can capture. So basically we are getting both type of signals, that is electrical and optical signal. So previously we were using a filamentary plasma source to simulate LEO-like conditions, but in the filamentary plasma source we had several problems. So in order to overcome those problems, globally people are using microwave-based plasma source. So our colleague from IPR, Mr. Sudhir Singh Wala, Dr. Rajesh Kumar and his team, they have developed this source indigenously. So basically we have approached several international companies, and nobody has supplied this source to us because of strategic nature. So finally, indigenously we have developed this source in our center. So this is a flood beam electron gun. So here you can see the energy of this beam is 200 eV to 30 kV, and the total spot size is 450 mm. So this 450 mm is sufficient to cover a coupon size of 300 by 300 mm, which basically we get it from URSC. So this is a spot size of electron gun. So it covers the entire coupon of, as I said, 300 by 300 mm. Now what happens once the coupon is charged? Then we have to measure the surface potential. So this is a equipment which is called as a electrostatic voltmeter. Fortunately, we have Mr. Nandakishore from Circuitech. So he has helped us to get this equipment some 12 years back from USA. And after giving the service of almost 12 years successfully for the several experiments, now there was some fault, and he has taken a personal initiative, and he is he's working on it. I think it is repaired, no? Completed, very good. So maybe by next week or so, it will be here. Thank you very much. So as I said, it was animated slide. So in order to capture all the data equations, electrical and optical signal, we have a national instrument-based data equation system. So there are different type of cards by which we can capture the electrical and optical signals of this experiment. So this facility you have already seen, so I will skip this slide. So now what happens whenever we perform this type of experiment, then huge amount of data is generated. So it becomes very difficult to sort out or identify the useful data information. So in this case, whenever we get a coupon, we enter different type of information from which type of experiment needs to be performed, what is the coupon specifications, and what are the data acquisition parameters. So based upon these input parameters, automatically one folder is generated, and all the information of that experiment has been stored in that folder only. So it becomes very easy, say after 4 or 5 years, if we have to extract the information. So based upon this automatic numbering, so it is a person independent record maintaining system, and it is very easy for us to identify or track the old record. So this is a graph which shows in my previous slide, as I've said that initially, whenever there is a shower of electron beam, so the coupon gets charged. So in this case, around 4.5 kV it is charged. Now what happens because of the insulating nature of the solar panel, there is a secondary emission. So you can see the potential has been reduced from minus 4.5 kV to around 3.7 or 3.8 kV sort of thing. So basically there is a difference of from 3.8 kV to 4.5 kV. So because of this inverted potential gradient, the arcing happens, and then you can see again the charge is getting neutralized. So as I said, for any space industry, it is very important that once they design the solar panel, then they would like to understand where are the arc probable locations. So they need this sort of information under both the category like LEO conditions and GEO conditions. So here we have performed an experiment for the LEO condition, and you can see these are the arc prone zone. So once if we get this information, we share this information with the space industry people, and then they modify their design accordingly so that the arc can be minimized. This is again a result of a geo experiment, and you can see these arcs location and arc coordinates are provided. This is a basically permanent sustained arc. These are the most dangerous arc because it can puncture, it can interrupt the electrical supply to the payloads. So this is an integrated image because as I said in my previous slide, there are 4 types of arc as per the ISO nomenclature. So the shortest duration arc is called primary arc. It is of the order of 1 to 5 microseconds. Then there are some around 10 to 20 microseconds. These are the temporary sustained arc, which are of the order of few tens of microseconds. And these permanent sustained arc are very dangerous, which I said earlier. So in this integrated image, you can see the blue dot represent the primary arc, green dot represent the non-sustained arc, and the yellow dot shows the temporary sustained arc, and this is the PSA. So if PSA happens, then it is very dangerous for any solar panel designer, and they would like to avoid such type of design. So because we also, since we capture all the information, so sometimes we also try to understand why this arc happened at a particular location, and we also try to propose some mitigation technique. So in this particular case, you can see this black one is the solar cells. You can see at the corner, there are some arc spots. So then we realized the corners facing each other are basically arc prone zone, and we have also seen that even the distance was more compared to the other experiment, but arcing was happening on this side. So we have proposed one arc mitigation technique that all the corner should be covered with the RTV solutions, and we are hopeful that arc should reduce. But in order to validate this design, we have to conduct several experiments, and maybe we will try to explore it on in the real life situation also. The second possibility is to just make a offset arrangement so the corners of the cell doesn't see each other. So this is the second mitigation technique which we have proposed. So as my previous speaker has said that government of India has started opening up the space sector for the startups. So recently, I think Mr. Vishal is here. So they have approached us to validate the design of their solar panel. So they have placed an order to us. Basically, I think he is going to cover the Dhruva space, about the Dhruva space, but this is the result which we have, we conducted the test in our facility, and the threshold arc voltage was 111 volts. So I would just like to conclude, because we are already delayed by half an hour, that the arcing is a very important phenomena in the space industry, especially on the satellite solar panel or harnessing. So we have to have a facility like this ISO test facility in which we can check what are the arc probable area and how to overcome this type of arc related issues. So particularly as such, this SPIX facility is concerned. So it is a completely automated facility in which we can detect the electrical and optical signal, and we can also differentiate different types of arcs. So if you see globally, if you see again it was animated slide. So this is a facility which is in the NASA. This is a facility in Europe, and here I have shown the facility for Japan and the China also. So we are fifth on the global map with having the ISO 11221 facility for the testing of solar panels. Thank you.
The platform is now open for some questions.
So basically, primary arc means the duration is very short, very small, maybe 4-5 microseconds. TSA is little bit more, maybe around 10 to 15 microseconds. And non-sustained sustained arc, sometimes these are. So here, the very short arcs. So blue one is the primary arc. So nobody can stop the arcs because it will happen. But we have to see that whether this type of arc should not happen. The last one. Yes, sir. Yes, madam, I think she will going to cover. Yes, you are right. Yes. Yeah. Yes. I think that part they take care because they take the cells from the same batch. Am I right? You are right. It can happen. I think that she can tell about the scanning method. That is true that it can happen. This is the thing. Yes, sir. Yes, sir. Yes, sir. Presently not, but we are planning for the future experiments. Yes. Yes, you are right. Yes. Yes, you are right.
be presenting about the spacecraft plasma interaction studies, which Dr. Gupta also presented, but I'll try to keep my talk as much as possible away from his lecture. So this is the agenda that I'll be covering. I'll be introducing about the space plasma, its impact on spacecraft, what are all the failures that has been reported in multiple literatures. I will also talk about the multi-junction solar cells that we presently use, the charging mechanism in our array, arcing, and what are the arc mitigation methods that we adopt, and what we could achieve from the SPICS facility from its inception and the present progress. What are all the major results and innovation that we could achieve from this facility and future scope? So just to introduce about the space plasma, there are the multiple sources of space plasma that our solar arrays encounter during our satellite life. It is generated by the solar energetic particle, which are part of the solar flare, protons, electrons, everything. There is one more source, which is the galactic cosmic rays, and also the ionospheric plasma, which is the evaporation of the ions into the atmosphere at low altitude, like 100 to 500 kilometer altitude. These are the sources of the plasma. It is getting more complex due to the magnetic field. The Earth's magnetic field is a major contributor to the trapping of this charged particle around Earth. So we see the trapped electrons and protons in the multiple layers above the Earth in the Van Allen belts, and there is also this Van Allen belt also shields the human space or the life within the atmosphere from these charged particles, and it also shields the LEO atmosphere or LEO environment, LEO satellites, and low inclination spacecraft from the solar flares and cosmic radiations. The trajectory of the electrons or the photoelectrons, that also gets modified by the magnetic field. Also, it induces the field effect when a large satellite moves through the magnetic field in the low Earth orbits. So all these modifications happen due to the magnetic field effect of the Earth. You can see here that if there is a secondary emission happening parallel to the magnetic field, the electron escapes. Whereas if there is a magnetic field perpendicular to the surface and the electron gets emitted, it due to the magnetic field effect, it has to enter back into the surface. So all these effects are created by the magnetic field, and this becomes very critical in low Earth orbit satellites and its plasma environment modeling. So right now we are addressing in our SPICS facility about two of these scenario. We are either working on the LEO orbit, where the plasma density is very high and the energy of the plasma is of very low range, or we are simulating the geosynchronous orbit or geostationary orbit kind of environment, where the plasma density is extremely low, but the energy is high. So these are the two scenarios that we simulate in the SPICS facility. And though there are multiple other orbits that we work on in ISRO, other orbits are LEO sun-synchronous polar orbits, where most of our cartographic ocean-sat series of satellites work, and LEO low inclination orbits like Gaganyaan, Astrosat, Megatropics. They all can be categorized as low inclination orbits, and geo orbits, geostationary or geosynchronous orbits, where our communication and navigation satellites are stationed. We have also other inclined orbits, where like microsat orbits, we have interplanetary and lunar mission orbits, and other orbits like L1 Lagrangian point orbits. So though multiple types of orbits are there, right now we are working in these two orbits, and we have tried to simulate the effect of plasma in our spacecraft and especially solar array. So how the plasma can affect the spacecraft? So here multiple types of the impacts are addressed. The first impact is on the electronic components or electronic gadgets, where a single event transient can happen, or a latch up can happen, or a single event burn. These are activities that can change either the status of certain binary elements or create some damages. It also adds the radiation accumulation on the electronics so that it will approach the radiation dosage to which it can survive. Beyond a certain radiation exposure, the electronics tend to fail or its performance degradation happens. So that is another effect. There are other effects which are very not much probed, like false information from sensors and the radioactive changes of certain components. So these are not very much studied. And other kind of changes are some surface property changes. There are multiple material used in the satellite to modify the surface properties of certain material, like thermal material or optical material. All the property changes due to the exposure to radiation. So these are some of the effects. And these are the two effects where we are very much interested. One is the power reduction due to the radiation which is falling on the solar cell. It can create damages like ionization damage or displacement damage, due to which the performance of the solar array gradually decreases, for which multiple models are available, and we take that into our design. And this is the major part which we are collaborating with FCIPT and trying to study, which is the RQ. Now, this is some history which I want to tell. Sometimes in the 90s, when the worldwide commercial satellites, they changed over to 100-volt bus, 120-volt bus. Suddenly, the number of failures on the solar array started to increase. You can see the kind of statistics. You can see that the maximum number of failures that have been reported are on the solar array. Either the satellite solar arrays were partially lost or fully lost. And this escalated the insurance cost like anything. And some of the major insurance company, they refused to insure the satellite solar array. So subsequently, the major, that is space community, they initiated that, yes, there should be a standardized testing method to evaluate the satellite solar array and ensure that that is going to survive in the plasma environment. That is how ISO 11221 came into being. And as part of the development community, we were also closely monitoring, and we could work with them. And even with IPR, we could easily change over our facility to an ISO certified facility. So just to introduce on the solar cells we use. Earlier, we were using silicon solar cells, which were single junction solar cells, where this is the kind of interface that we have. It is a single junction PN junction where an incident light converts into a electron and a proton pair, and the inherent that is a space charge separates them, and useful power is generated. Here, if you see, this is the solar spectrum which is seen outside the atmosphere, called air mass zero spectrum. And here, a single junction solar cell can use only a part of that spectrum. Whereas right now, whatever cells we are using, it has multiple cells or a tandem cells. All are based on the gallium arsenide cells. So you can see the top cell is a gallium indium phosphide cell, and the middle one is a gallium arsenide, and the bottom cell is a germanium cell. And if you see, when air mass zero spectrum falls on it, the gallium indium phosphide uses spectrum, this first portion, blue portion of the spectrum, up to around 0.7 micron. The remaining light is passed through, and the green cell works in this particular zone, and it captures the energy up to around 0.9 micron, and the remaining energy from 900 nanometer to around 1800 nanometer is captured by this red cell or the germanium cell. So you can see that all the three cells are using different spectra of the sun, and the more or less the full spectral range is captured. So the top cell, middle cell, and the bottom cell, the gray, blue, and red, so the green, blue, and red, they together give this this IV or the current voltage plot, which is generated from the multi-junction solar cells that we use. So when the silicon cell we talk about, it can generate say 0.5 volt as the terminal voltage or the open circuit voltage. Whereas in the multi-junction cell, we are getting around 2.7 volt as the single cells voltage. So when we use such high efficiency cells, we also have to ensure that each of the circuit is protected and we do not end up in problems like arcing. So if we expose a solar array in an space environment, what are all the mechanisms that happen and how the charge buildup happens? So the charge buildup can be due to the electron deposition. The charge can escape, or the negative charge can escape by backscattering. There also are material which are having a very high secondary electron emission property, and there can be field emissions, also photoelectric emission. So all these things contribute to the charge buildup on the solar array. So if this I is the current due to this charge accumulation, the I is the algebraic sum of all these, where this is the electron deposition charge, this is minus the ion deposition charge, secondary emission charge, field effect, backscattering, and photon electric charge. So in an equilibrium, all these things will be balanced, and the net current coming or escaping the solar array will be zero. And as Dr. Gupta told, as the satellite is exposed or placed in the plasma environment, the satellite and the solar array starts to accumulate negative charge, because more of electrons will be able to charge the surface of the satellite and the solar array. But after a certain time, the cover glass will start to emit the electrons back, or secondary electron emission happen, and inverse potential gradient develops in the solar array and the spacecraft. So this inverse potential gradient is responsible for the primary or the secondary arcs that is happening, and the charge settlement happens. So why the solar array starts to arc? So for that, there are multiple reasons. The first reason is the material choice. To survive the kind of system that we have to see in space, we have to use multiple types of material. So this is a solar array substrate, where the topmost layer is a very highly insulative material or a kapton material. That is one of the sources where, one of the regions where charge buildup can happen. And also you can see individual cells are sitting on the solar array, and the topmost layer is a glass layer, which is also an insulating layer. And you can see there is a cavity through which the cells are connected to each other in series. And so you can see there's a cavity in which either it is vacuum, or some contaminations are sitting over there with a conductor and an insulator nearby. So these are the kind of nooks and corners which is promoting the arcing which is happening on the solar array. So the first thing which is going to make the solar array charge and arc is the material choice itself, like the electrical blanket design and the exposed conductor. The second one is the bus configuration. If you go for a very low bus voltage, the chances that your material are susceptible, and the chances of arcing is very less. So, but however, now we are moving towards high voltages of the range of 70 volt, and in future in 200 and 120 volt. So we have to necessarily go with the market, and we are also moving towards that. And another thing is we have to limit the current that a conductor or a solar cell can carry. If these two are not controlled or not addressed, there can be a chance of arcing. The third thing that can lead to arcing is the contamination. So what is the kind of material that you choose to make the solar array? Every material you ensure that it is meeting the ASTM E595, so that the mass loss and the contamination or the condensed vapor is very low. And also you ensure that during your process, no contamination is included in the material. That is, nothing is able to get trapped in your system, and avoid the triple point. These are to be handled by our process. And if these things are not handled, the array which will have the primary arc can lead to temporary sustained arc, permanent sustained arc, and subsequently pyrolysis, where the everything in this Eureka satellite retrieved solar array, you can see that every interface in the solar panel has been damaged due to this arcing. The solar cells, the metal, as well as the substrate itself, everything is involved due to a very large energy flow. So how this energy arc is a simple readjustment of charge. Whatever charge is accumulated in the insulator is getting discharged through the nearest conductor. So from where this much of energy is obtained, that is from the solar array itself. The array is generating power, a very high energy is getting generated. That energy starts to flow through this arc or this defect zone, and it is able to reach its bus negative or the ground. This generated current will keep on flowing through this till this area is damaged. So this is what we have to avoid, or we have to work towards to mitigate. Whereas primary arcs are always keep happening on the solar array, we have to live with it. We have to ensure that our array is robust enough to live with the primary arc and avoid the permanent sustained arc. Okay, there is this region. You can see that it's a very small region where you can see an insulator, a conductor, and a cavity where a plasma can get trapped. So assume that it is as freshly launched satellite in which this kind of a cavity is left out. All the material, they are having some contamination, say some low volatile conductive gases that keep evolving, because the satellite and the solar array is outgassing as it is exposed to vacuum. So the whole area will be having an envelope of evolved gases. So in this small area, there are 3 points. One is a charged insulator, there is a plasma, and a metal. The metal is nothing but the satellite bus. So the whatever charges that are accumulated, it will find a path through this plasma and enter into the satellite bus. This path is enabled, that is called a triple point. Finally, it will be a line, but we call it triple point because it's a volume. To a certain extent, it helps, because initially when you are making the solar array, there has to be certain usage of volatile chemicals, which will not be immediately able to escape. Instead of allowing it to escape after exposing to the space condition, you try to avoid or eliminate it in the vacuum test. So a vacuum bake will certainly help, but something like moisture ingression and all, again, it can accumulate, which will finally be outgassed only in space. So these are the major arc mitigation techniques that we adopt in the satellite solar array. First of all, we ensure that the material selection is proper. So all the material that we select should have the proper dielectric properties. And also we ensure that they are all meeting the contamination control guidelines to a very strict extent. If ASTM E595 insists that it should be 1% and 0.1% of TML and CBCM, we go one grade higher of 0.1 and 0.01, so that our solar array is clean in all respects. The second activity is deep vacuum and outgassing. That is the same point which I told. Also, just now, whatever our friend was indicating, that we do a deep vacuum exposure, so that whatever residual volatiles are there, we try to remove it from the system. The third thing is that in spite of doing all these things, there can be some micrometeoroid impacts as we launch the satellite into the space, and the solar array does not have any protection. It can anytime get impacted by micrometeoroids. And generally, the micrometeoroid impact will immediately create a very big plasma plume around the center of damage. So we have to isolate the mechanical damage and ensure that electrically it is not able to contribute to the secondary arc generation. So this has to be done by design and isolation. The next thing we have to take care is better electrical design, in which we are able to current limit in each of the paths. So each of the electrical circuit or the electrical cell circuit in series, we are ensuring that beyond a certain amount of current, even if a fault current tries to flow through it, it is not possible. This is done by diode isolations of each of the circuits. We also do certain modifications in the layout to ensure that differential voltage is reduced between nearest points. To avoid triple points, we do a process called the grout. We embed the triple point zones with dielectric material so that accumulation of the plasma in such zones are avoided. We also take care that exposed conductors are also embedded in this dielectric. Though we do all these things, we also have to ensure that this final process has to survive the temperature the solar array is supposed to see, and also survive the number of thermal cycles it is supposed to see. So these processes, what we employ on the panel or the coupon, that we test in this ISO facility, as well as life cycle test in URSC, to ensure that this survives the plasma avoidance or the arcing avoidance, as well as proper functioning at the end of electrically and mechanically. It survives this many number of cycles at this temperature escalations. So as I told, we also model the arc, that is plasma environment, and subsequently all these configurations are tested and demonstrated and validated in the ISO facility that is established by SPICS. So I will skip this slide because many people have already spoken about it. But I will just specify that we started with the LEO facility in SPICS 1, where LEO plasma was modeled, that is realized. And in SPICS 2, we upgraded that system to ISO standard with a geo kind of environment with the electron gun. And we have conducted more than 50 experiments in that SPICS 2 facility. Now we are working with the SPICS team again to upgrade the system to meet 100-volt bus development, which is happening parallelly in URSC. And based on the feedback that we received from SPICS 1, these many satellites we have already realized, and they are in space. This is just to show some grouted and ungrouted configurations. Many people have spoken about it, so I will skip these slides. And these are some of the results that we obtained from SPICS facility, a permanent sustained arc. And this is the charge buildup that happened. And these are some curing experiments, where if we expose it for more time in the vacuum and chamber conditions, we are seeing it less and less. And these are the probable arc locations, which already Dr. Gupta has explained to you. And this is another interesting result, innovative result that we obtained from IPR facility, where certain points in the solar array was advised to be spotted so that it can act as arc mitigation. We have supplied a coupon fabricator to this level, and the results are available. Now I'll just speak about what is the future that holds for us together. So though we started with such small satellites, now we have propagated to satellites where big solar arrays are there of the order of 70 meters square. And we have already successfully demonstrated that our 70-volt bus is successfully deployed in orbit for more than 5-6 satellites. And there are no arc-related or arcing-related observations in our solar arrays. Now we are moving towards 100-volt bus development. So we are working closely with SPICS facility to test our configuration for 100-volt survivability. And in future, as Mr. Schonberg also told, that we are moving towards electric propulsion systems, and we'll be raising our orbits from the geosynchronous transfer orbit to geo orbits using electric propulsion. We need to study the modified plasma environment created due to this kind of ion thrusters in our solar panel environment. How the presently modeled plasma gets modified, this needs to be studied. Are there going to be any erosions in the solar array interfaces? Whether the glass will get eroded, we have to study on that, as well as how the optical properties are going to change. So these are some of the areas which we would like to work closely with FCIPT. And we are also going towards high power flexible solar arrays. We are working on roll-out solar arrays, fold-out solar arrays and all. And the technology is getting evolved in URSC, and we'll be demonstrating the flexible solar array by 2024. And the array may look like something like this, which is the ROSA panel, which was deployed in ISS last year. So if this is the kind of panel where there is no substrate, and mostly there are only some membranes on which solar cells are bonded, how the plasma environment will be and how we can mitigate the plasma interactions. That is a study on its own, and we'll be doing this in future. And also the micrometeoroids and the debris impacts. This also is a good study. We are now trying to model it and study. And we are also interested to study on the SSPO orbits, which are having high energy and high density plasma, which so far we have not addressed. So these are some of the studies which probably we can work together in the future. So with this, I thank you, audience.
In some of the studies for intergalactic missions and all that, design studies, the very high energy charge particle damage was a problem.
Yes.
So they come out with ideas of generating magnetic fields to shield the spacecraft. So is that something that you're considering, possibility of using magnetic fields to trap the incoming electrons so they do not touch the surface?
Sir, right now we are not working towards that because we have already realized our lunar missions and Mars orbiter missions, which are very near to Earth. And we know the kind of energetic particles that are in these zones. And we did not consider any mitigative techniques. However, we designed our solar arrays to perform even if such radiation particles are encountered. So the array was designed for such degradations. So that is how we have.
Futuristic.
If we are planning some missions towards up to Jupiter, yes, this kind of a study will be required because Jupiter has a very, very, very strong magnetic field. Yes, it will be required.
Actually, for our high resolution satellites camera, so there we use our detector, basically focal plane. So it is a very costly item, very sensitive. So if detector goes off, then whole mission will be off. Okay. So they are very sensitive to high energy particles and all these things. So we are using basically some sort of like high density tantalum metals shielding port, particularly that detector location, which is very small. And maximum only 240 mm kind of thing. But I will show you that. Yeah. Yes, it will not, by CCD pixel, it will not.
Madam, as I see that already the bus voltage is about to reach 100 volt. So I feel that glass is more resistant towards the radiation effects, but silicon as well as the grouting material at 100 AV, I expect that a lot of changes are expected in grouting material. So we can plan this kind of experiment using our existing facilities, as we already discussed. So what kind of other radiation experiment you are planning to do testing in future? Because we have other DAE facilities and we can even do the defects analysis in the semiconductors. We have those kind of facilities in other DA institute. So what you are looking for in radiation exposures?
So right now we are looking at some 3 different kind of studies. Along with FCIPT, we are already studying the spacecraft plasma interaction. And we are already collaborating with other BARC centers where particle irradiation facilities are there, like proton and electron irradiation facilities. We buy the solar cells from reputed manufacturers, and they already have studied its radiation tolerance and radiation degradation characteristics. However, we are right now trying to collaborate with BARC facilities and trying to irradiate the solar cells with multiple energized particulates to validate, to make our own models, as well as to validate the results already provided by the vendors. This is performed to cater to the future requirement, where we are going to make our own solar cells within the country. So we should have the end-to-end process how to evaluate our own solar cells at when it is getting exposed to radiation. So this is the second kind of collaborative work which we are doing. The third kind of work which we are envisaging is the atomic oxygen and UV exposure. So whenever a satellite is going to the low Earth orbits, from 100 kilometer to 500 kilometer, there is a very highly reactive species of atomic oxygen, which can interact with the solar array and as well as other thermal coatings or exposed polymers and other material, and can oxidize the surfaces. So there are some collaborative work going ahead in BSSC as well as with Pune University, where we are planning to establish a facility to facility which can have 5 eV atomic oxygen source. So all the surface treated samples of satellite, we can irradiate in that facility and ensure that the protection coatings are taken care. So these are the kind of facilities. Thank you. Yes, initially when the Leo plasma was initiated, even SPIX project, they themselves were able to make a rudimentary model. And subsequently, we have collaborated with another company named Samstra, who have now developed the model to that is simulate the charging characteristics of the solar array. Leo charging model and the geo charging model has been made, but the arcing model is yet to be there. Next speaker is Dr. Brennan, and he's going to talk on mechanical design of space telescope and interactions with ideas for plasma applications in tech and without cable. And I appreciate it.
My topic is basically mechanical design of space telescope, and we have been interacting with the plasma, that is our FCIPT, 3-4 years back with Mr. I think Dr. Nirav Rajpara and Mr. Ramkrishna Rane. And of course, recently we have got very good system from Ranna Madam, cryo pump, and we are again going to get a scaled up version from Ranna Madam only for our thermovac facility. So that is the thing. So since I spent 30 years in mechanical design of space telescope, I will be covering those things first and how we are utilizing, basically apply this plasma technology for our telescope. That is a basic idea. So ISRO, you know, we are in satellite business, making rockets, satellites, payloads, and we have different centers like rocketries and other things being made at VSSC. They are launched from Shar Sri Harikota. Then our URSC is a satellite making center in which we are fitting payloads. And Space Application Center, we are the main, जो गुजराती में बोलते हैं ना, वरराजा है हम, और हम payloads बनाते हैं, basically communication, navigation, remote sensing, science mission, Chandrayaan, Mangalyaan, all everything. And all these payloads, once we deliver to URSC, they are all being fitted on main satellite bus. And from there, it will be shifted to Sri Harikota. And on the top of the rocket, we will be putting all our satellites and launching into the space. So our main core competence lies in basically generating or understanding the requirements from Indian industry, that what kind of application they want. So we are basically interfacing between governmental agencies, various departments, and then we are understanding their requirements and trying to put or those things into hardware. That is basic our core competence. So these are rockets. So our Shanbhog sir and Krishna Priya, they are in this basically core competence. And this is the, this is where my payloads working at SAC ISRO Ahmedabad, that will be fitted over here. And at the top of the rocket, this is the top of the rocket, and where it will be put satellite, and this is fairing, this is covering, and then afterwards we are launching into the space. So my focus is on telescope. So telescope, they are basically giant eyes that can collect far more light than our naked eyes. And basically they are used for Earth observations. There are some special applications, weather forecasting, even galactic survey, astronomical purpose, and there are so many purpose for telescope. Different types of telescope. I will be touching like refractive. It is a lens-based system. Then you have reflective telescopes, and then for X-ray telescope you have simple. Because the signal strength is very, very less, you just have to divert those whatever signal in terms of like particles or X-rays they are coming or they are falling on the telescope. You just have to focus and just study those using detectors. So this is again the various refractive systems. Now, as far as you know, refractive system, any of the energy electromagnetic rays, they fall onto the lens and they will pass through the lens, and then there will be a focus for any of the optical system. Whereas in case of the reflective system, it will be rays will be getting reflected, and there will be couple of optical elements like primary, secondary mirror, tertiary mirror, and different types of system like Newtonian. You have focus on one side of the primary, which is a main aperture. Then you have Cassegrain focus, in which you have your rays getting focus on the back side of the primary mirror. Then you have Makutsav, Gregorian, Smith, and hybrid systems. Okay, as far as refractive system is concerned, you have very simple like singlet lens, achromatic, doublets, double gauze, and Cook triplet. Okay. Now, broad level, if you see across the globe, if you see any of the telescopes, you will find most of the telescopes are reflective type. Why? Because for any of the refractive system, you have to have a very transparent, particular shape, honoring mathematical function like hyperbola, parabola, or ellipsoid kind of things. And it's very difficult to make, because you have to have accuracy of the order of like nanometer level, 11, 12, 15 nanometer kind of RMS, it is very difficult to generate. So even in across the globe, largest telescope with refractive system is only 1 meter diameter, that is with US only, number one. And most of the system, if you see, including any of the space or ground-based astronomical telescope, they are running into like 6 meter, 12 meter, or combination of so much interferometry on ground-based telescope. So that is the beauty of reflective system, that you are worried about only on one side, that is reflection of rays only. Back side आप कुछ भी रख लो तो भी चलेगा. So that is the idea of reflective. It is very easy to fabricate, very easy to design also. Okay. And refractive system, again, you have disadvantage like chromatic aberrations and all other things. So that you are trying to, that you are also avoiding by going for reflective system. So today I will be mostly talking you about the reflective system only. See, refractive system, it has also got its own advantage. You will have very wide field of view. But in case of the reflective system, your field of view will be very narrow. It will be terms like arc minutes or degrees only. Whereas in case of the refractive system, any small system like 100 mm diameter, 160 mm diameter, you can have plus minus 30 degree. So you can at a time cover a very large area on the earth or any area of interest, whether it is border area or anything. So this is again a Newtonian telescope. They use M1 as a paraboloid, M2 is a plane mirror. Then Gregorian, you have paraboloidal and ellipsoidal. Then Cassegrain, you have paraboloid and hyperboloid for primary and secondary. To make presentation interesting, I'm not going in a theoretical like what college, what we are being taught. No, these are the first orders, integral, derivative, and all these things. I'm going the reverse way. Whatever we have made, ISRO has made. So straight away, I'm throwing you the photographs of actual system. And then slowly we will, at the end, we will come to know this is the actual requirements. And parallelly also, how plasma we can make use of it in a better way for our application. So basically, telescope function is holding all the optical elements. You have so many mirrors, lenses, and it will maybe like combination of mirrors and lenses. You have to hold them properly. If you take any small Nikon or Canon camera, the aperture will be like diameter, 1 inch diameter, 25 mm, 30 mm, or 50 mm. Okay. Whereas we are making satellites or cameras with diameter ranging even up to 1.2 meter. And slowly we are going in the JWST range. Okay. So that is the thing. Of course, those 6 meter or 3 meter kind of diameter mirror that we are going in segmented mode. And then that we will be combining side by side with accurate positioning and all these things to ensure ensuring better image quality. So that is the idea. Now, as far as structure is concerned, we have main cylinder or metering cylinder. As I told you earlier, I showed you some of the like Newtonian, Gregorian, then Cassegrain kind of telescope. You have primary mirror and secondary mirror as your main optical elements. So separating this element, you require basically main cylinder or metering cylinder, we call it, which is the main, our critical element as far as mechanical engineering point of view. Second thing is main bench or platform. This is the platform on which we will be putting or fixing our primary mirror, which is our primary aperture. And the quality of this aperture, whether in terms of diameter or its surface quality, that will decide basically your overall telescope performance. So it is a main critical member. Then you have struts and truss. Why we are using struts and truss? Because we have to have very good accessibility from assembly, integration, and test point of view. Third thing is mirror optics. Of course, these are very critical things. And we have to go for semi-kinematics kind of things. So as a basic mechanical engineer, as you know, if it is a statically determinate system, it's fantastic. You have number of solutions equal to number of unknowns. Okay, equations. So that is the ideal system. And mirror and this basically reflective system, optical system, the peculiarity, it is highly brittle system, number one. and it has got a very low strength, 10 MPa kind of thing. So that is 1 kg per mm square only. So even fabrication itself is a big challenge. Okay. And moreover, when we are making these mirrors and all these things, we have to mount it properly. And for any optical system, their positioning stability is very, very important. Okay. So their mounting schemes and all other things, they are to be designed in such a way that during that 15 or 20 minutes of rocket vibrations, it should be able to survive. That is a basic idea. Then you have detector mounts. Detectors, they are very costly. It is basically semiconductor, and nowadays even Taiwan is holding the key across the globe. So that is a very crucial thing. Then you have focal plane assemblies. So detector mounts combined with the high-speed electronics. When you are going for spatial and strategic applications, when our satellite is traversing like from Kashmir to Kanyakumari, you are left with only 10 or 15 minutes. So within those time, you have to have all the data. And that data, uski jo freshness hai na, that is very, very important. And you have to not only take the images very fast, but you have to send, and then there will be cascading effects, maybe any kind of things. So you require all these things to be assembled in a small box kind of things. So that is very challenging. And detector, as I told you, it's very costly item. It has to survive my rocket or launch loads. They are of the order of like 15 times of gravitational accelerations, which is now 9.81 meter per second square. So it has to survive those loads, which we call it steady state acceleration loads. So mount design, material, everything we have to. And not only that, once it goes into the space, the other culprit is on one side we have sun. Okay. Direct you have sigma 8 e raised to 4, that is radiation heat transfer. Okay. The other side is 4 Kelvin deep space. So there will be very large temperature excursions. Okay. So to take care of that, we have to go for proper material selection also. So these are again straightway telescope, which we have launched in 2005. And it is a series of telescope. And they are giving us very good images continuously. Such type of things, we already have 3 numbers. Now here, if you see carefully, as I told you, this is a Cassegrain kind of system. This is my primary mirror. This is secondary mirror. And on the back side, we have here focal plane assemblies. Okay. Here the mirror diameter is 0.7 meter, 700 mm diameter. And my secondary is around 200 mm diameter. The length of the telescope is 1.2 meter and total is about like 1.4 meter. So this is one such to feel you, to sensitize you what we are actually doing. That's why I'm directly showing you all this in a cutaway view. So any mechanical engineer or optomechanical engineer in SEC, ISRO, Ahmedabad, they will be getting ray diagram from the scientist people. They are the real, means they will be designing some scheme of where it should be like primary mirror, secondary mirror. So everything will be in the air, to be literally in our crude language. Okay. Then they will simply tell, okay, you give us this thing. Anywhere, that is none of our business, that is your business. Okay. So then we have to start building basically surrounding structure to hold all these things. Now here also, if you see carefully, this is my focal plane. So that I have done exploded view of over here. Now here interesting thing is, if you see it over here carefully, my total optical system will be getting focus at the focal plane, which we call it as a detector plane. And detector availability, because since it is a ceramic material, the length availability, there is a length restrictions on the side of detector. Like you cannot go beyond 120 mm or something like that. But at the same time, suppose you want to have more coverage on the ground at a time, suppose you want to say 120 mm detector, if it covers like 12 kilometer footprint on Earth, and I want to cover at a time, suppose more than that, then accordingly I have to arrange number of detectors side by side. So this scheme also we have to give, which we call it as a optical butting. And in optical way, by using various prism, we are putting like offsetting one like this, then like this, like this. So 90 degree, it will be orthogonal. And we have to put in a prism extensive use of prisms also. So all these things, they are very small spaces. So within that, the mechanical engineer has to play. He has to build material and clearing the rays for basically it is the signal which matters. So I should not design any mount or anything which should obstruct those rays because it is my basic input. So this is this type of 3D model we used to get from our optics designer. And based on this, it is not that they also will be giving us some 3 or 4 different schemes of optics. And then we also sit together cohesively and we can also suggest that why don't you go for this type of configuration, and so that our life will be easier. That is the basic idea. So this is anyway cutaway view. If you see here carefully, the top, this is my total CFRP cylinder, carbon fiber reinforced plastic. And this is my primary mirror. This is my baffle, we call it. So earth radiation will fall directly onto primary mirror over here. Then it will be directed to go to secondary mirror. Then in the center at the bottom, at the focal plane, what I show you, without any mechanical mounts or anything, there it will be getting focused. And there will be reconstruction of images because it is basically electromagnetic radiation which will convert either photons into like current or voltage, and then it will be through electronics processing back end with high speed electronics, we'll be able to reconstruct the total image. So here if you see, again same thing to sensitize you more about, see, earlier we used to go for like metallic materials, aluminum, Invar, even SS and all these things for our earlier missions. But since our it is the launch cost which also matters, because per kg launch cost is running into like $12,000 to $25,000 per kg. So every gram saved from payload side will definitely save. It will have cascading effect on my satellite bus as well as to launch vehicle capability, and thereby it will increase my mission overall capability also. So that is the basic idea. So if you see, there are, again, I am throwing the same thing again and again on you to make you more involved in my mechanical design. This is my basically CFRP cylinder. This is my ring. This is basically for stiffening. And this is my spars. And why I am putting only very thin spar over here? Because my target is to collect as maximum radiation as possible from the surface of the earth or from the area of the interest. So our target is basically, it should not be more than like 3%. The footprint of this thickness, this spars, it should not be more than 3% of the total incident radiation. Because anyway, my secondary mirror, it is already obstructing my primary mirror line of sight. So that way my signal strength is getting reduced. So to avoid that, this is basically, here comes what mechanical engineer comes. So this is again preliminary with textbook formulas. We have like cantilever beam, design PL cube by 3EI. Then you have simply supported beam and all these things. So with primary formulas, you have some thickness of the shell, okay? Then thickness of your this main base plate on which we are putting mirrors, okay? So all these things will come. But afterwards, to have the accurate design analysis, we are using various codes like Nastran, Patran, then Hypermesh, 3D modelings, and all these things. These are all basically processing softwares we are using to validate our design. That is a basic idea. So if you can see over here, this is basically my breathing mode of the cylinder. Because if you see over here, these are all my anchoring points, and this is a cantilever beam, okay? And my fixation point is only from this point, because any of the optical system, when we are talking about micron level stability, okay, you have to have you can say adequate number of fixation point It should be neither more or neither nor less. If they are less number of fixation point, then it will be ultimately going to instability. And my optical elements, they won't be in their position. But the moment I go for over constraint system, then it will generate unnecessarily stress on my mirror. And if you see my any of the optical system, their active surface accuracy, they are running into like nanometer, 10 to 12 nanometer RMS. And I have to maintain during my imaging. And the other important thing is, like suppose I have these two mirror. This is secondary mirror. Here I have got primary mirror. So stability of this mirror, if it gets changed by even 1 micron, my focus will be out by factor of like 20 or 100. Because the more, if you are going a high resolution system, satellite, like suppose from 350 kilometer, I want to read number plate of particular vehicle. Okay, then I have to have a very large mirror. And the system also should be very sensitive. So sensitive means ultimately it will get converted into mechanical engineer. There will be more challenge. He has to go for material of like this metering cylinder, which should have CTE almost tends to 0. Because as I told you, once we go into the space, we are subjected to severe temperature excursion. On one side, you have 5000 degrees centigrade ball, that is sun. Other side, you have 4 Kelvin. So it's a very large temperature excursions. Of course, we have different mitigating effects, covers, MLIs, Kapton taps, and all. Sheets are there. But at material selection level itself, we are trying to solve this problem. That is a basic idea. This is deflection. My first fundamental mode actually. So generally, our space-based system, no, they are stiffness-based design. So we are basically limiting elastic deflection. If you know single degree of freedom system, Fn is equal to 1 upon 2 pi under root g upon delta. So g is your nothing but earth gravity. And under earth gravity, whatever deflections come, that will decide. And why here it is important that our particular launch vehicle frequency along the axis, that is a longitudinal frequency, is around 11 or 12 hertz, which is very minimum. Okay. And accordingly, when we are going for like satellite fixation on top of the rocket, it should be like separated by 1 octave. By factor of ideally, it should be √2. But to be on safer side, we are going for factor of 2. So √2 comes basically from your single degree of freedom system transmissibility versus response curve, where beyond √2, that is your forcing frequency to natural frequency ratio, if it gets more than √2, then all your amplification will be less than 1 only. That is a basic idea. So this is once again, recently we launched this Cartosat 3. It is a special strategic application satellite. And if you see here how complex the system is, because for spatial and strategic application, you are interested in giving data to some special people who are the decision makers in within very short time. Otherwise, those people will be acting very fast and there will be cascading effect. So all these detectors and all these things, they are so complicated. It is so messed up over here that we have to play within that. So compared to other conventional mechanical engineering design, here the design starts from configuration stage, not a concept stage. As I told you, the first input what we are getting is basically optical ray diagram. And we don't have freedom that yes, you go for this particular lens over here or mirror over here. So what happens? Once they give us, we have to raise everything with 3% constraint, and around that only we have to build material and we have to ensure all stability, everything. That is a basic idea. So this is the model one for my finite element analysis as well as 3D modeling for layout planning. And this is the actual one. And it is already flown. And second one is also in the pipeline. So this is anyway ray diagram I already told you. So this is one such in the basically assembly stage in our SEC ISRO Ahmedabad facility, clean room. It is class 10,000 and everything being done over here. So here, take a word from me that metal is slowly getting replaced in all our, it is being replaced by plastics only. That's why we need your help. Because what happens, broad level aluminum is having density 2.7 gram per cc. But again, that alpha fellow is very adamant, 23 into 10 raised to minus 6 per degree centigrade. So we cannot use. Similarly, if you go for like CFRP, carbon fiber reinforced plastic, you would have 1.6 gram per cc and you can tailor the property. And fiber alone alpha is minus 1.5 to 0.5 into 10 raised to minus 6 per degree centigrade. So even though resin alpha is very high, fiber is basically controlling properties, a structural member. So with that, but there you are getting disadvantage of basically electrical point of view, conductivity, your reflectivity and all these things. So for that we require coating. That coating has to be qualified, which is possible only with plasma. Coating on CFRP. Yeah. See here, one more problem is there. This cylinder, as you are seeing, we are using, I think, carbon fiber reinforced plastic. People are aware, as I understand. Fiber is a structural member and resin is for holding the fibers. Okay. And fiber along the direction, it has got wonderful properties, excellent tensile strength, stiffness, everything fantastic. Okay. But it has to be held by using resins, thermoset resins, epoxy. And it is a major weak element. Okay. So what happens during processing on ground, there will be moisture ingression inside. Okay. And our optical system, even between two optical elements, even a micron instability will not give a good performance for my image. Okay. So that's why this fellow, what it will happen, the moment it goes into the space, it is subjected to hard vacuum. So this moisture will try to dissolve. So however, the changes are not visible with our naked eyes, like a micron or 2 or 3. But my focus will be out because that optics design is like that. Magnification factor, then you have depth of focus 2 lambda f number square. Okay. So with that, it will be out. So in this case, what we have in our mind is just coat it with the metal and don't allow moisture to dissolve. So that whatever alignment we did in our lab, that will be intact. And we have to consider only that stiffness part. Because of the gravity, whatever loading, that only offset we have to be worried. That's all. So this is anyway backside assembly. These are different mirrors. Now this particular satellite is for strategic application and we use 10 number of mirrors. So any of the optical system like primary mirror, if you have 15 meter focal length, okay, this 15 meter focal length you have to achieve by using number of mirrors, because we don't have that big size of rocket top side, that much space available. So we have to fold it. Our design has to be very compact and it should be accommodatable at the top of the rocket. So we are using multiple mirrors. So this is anyway FE model, and our expertise at SEC ISRO Ahmedabad is whatever prediction we are getting over here, like 71 hertz, and we are getting 72 hertz. That is the frequency with actual vibration, taste, and all these things. So these are different modes like 30, 35.5, 42, different modes. So they will be moving in particular direction. Like when they are subjected to rocket or launch loads, they will be vibrating in this particular fashion. So I have to ensure that my neighboring elements, they also should not get hit. That is a basic idea. That is the reason why it is a stiffness-based design, not a strength-based design, what you are seeing on the on ground. So this is anyway different mode shape, and this is the cylinder we are developing with the Atira, because we in ISRO at Ahmedabad, or rather overall, It is always our cost cutting exercise, and we are trying to develop our indigenous technologies. So with Atira, we could develop CFRP hardwares, and that we have flown into 7 satellites, all space qualified. So this is one such vibration test, as I was telling you, that our rocket vibration, they should be able to sustain those things. So management will again ask us that you please demonstrate on ground. You have to qualify. So that thing we are vibrating over here in our SAC ISRO facility. And that again, as Vinod sir told, no, in space director, that now facilities are available for outside private players also. So that also, if anybody is interested, they can approach us. There is no issue. So this is anyway modeling part like GI set. So like we have low Earth orbit, which is ranging from 300 kilometers up to 900 kilometers. Then geostationary orbit, we have 36,000 kilometers. So why 36,000 kilometers? Because angular velocity of my satellite exactly coincides with the angular velocity of the Earth. So generally for communication satellite, we have to use. And it comes from that formula, Gm1 m2 by r square is equal to mv square upon r. Simple. So this is one of the GI set that we are also going to launch in probably mid of next year. And it will give you images in a fixed way, continuously. So like our low Earth orbit satellite, they will be moving from north, south, downwards. And we will have only 15 minutes window only for observing our satellites. Whereas in this case, it will be a continuous 24-hour vision. So this is anyway, same structures only. And CTE and CME, see here, as I told you, coefficient of thermal expansion is very, very important. Okay. So that by design, we are putting some fiber direction like 0, 45, 60, like that, quasi. Okay. And that we are validating by actual simulating the same in our thermal vacuum chambers. Okay. And we are subjecting it to temperature changes using some displacement capacitive sensors, inductive probes. With that, with 1 micron accuracy, and with that, we are characterizing that yes, whatever designing that we are achieving or not. So earlier in 70s, 80s and 90s, we were going for some INVAR, which is having 8.13 gram per cc, very high density. So structure was like 500 kg or something. So that was the thing. So this is anyway models sandwich. This is sandwich base plate only develop over here. Okay. We have developed with the Atira, with the help of Atira. Then when you are going for plastic, no, you have to use metal inserts over here. So that we have to use. So this is anyway sandwich construction. We have advantage of section modulus. When you are throwing more material away from the neutral axis, you can always have very high moment of inertia. So this is good for resisting basically. So this is again how we are making core, sandwich core from CFRP sheets. Same thing. And this is particular mirror interferometry we are measurement doing. And this is our migration up to 1.2 meters, sorry. So this is how, this is basically our semi-kinematic interface design. And this is a hybrid mirror. What we are planning is basically the top surface only will be like glass or metal, and that we will be coating with the reflective silver or aluminum kind of material. So this is anyway our structures only. This is for mirror mount semi-kinematic interfaces. So this is our like detectors, even though they are very small, we have to model it carefully because they are running into crores. And we have to isolate or base disturbances like temperature or structural by way of using these flexors. So this is anyway, I already told you that it is the basic of vibration only, that you have to decouple stiffness based design one over the other. So these are all, see, for material comparison, we have to make it on common platform. Okay. So that's why these are the numbers, like cube root of E by rho like that. So these are material comparisons, but nowadays we are converging to CFRP and some shape memory alloys and spatial alloys only. So this is anyway CFRP composite side. So this is also one such, this is the chamber in which we are testing, simulating hard vacuum of space and temperature excursion both. This is one such in progress. Okay. So plasma, these are the horns. We carried out coating. We gave this type of thing to Mr. Ramkrishna, and they also gave us inside coating. So that was okay. Even from standpoint of it is 3-4 times than our conventional things actually. CFRP, yes. It is coating silver. That they have done, I think, 8 or 10 engagement. कहाँ है रामकृष्ण? कितना? 8 micron. For not for stiffness, sir. Here it is electrical. RF. Because those mechanical things anyway I am getting from CFRP only. Coating is only for micron and that is for electrical purpose. Coating on a surface, metal coating on a CFRP, which is a plastic. So this is anyway our Kiran Kumar, no? He was my reporting boss. So this is, we are planning for basically big size terahertz in Hanle facility, where we have to shift all our materials. If it is metal, no, then it's very difficult. So we are planning. So for this, I have to put a word and interacting with Mr. Ramakrishna and Miran. So this is again, this type of waveguides, no, they are running like 30 or 40 kilometers per satellites. So that we are trying to convert to CFRP, and inside we are planning for basically this type of things, outside or inside, to make it electrically conductive. And of course, this is already done by Ramakrishna only. Carrier plates, I think you can remember. Or so this is anyway mirror. We are planning hybrid. Instead of glass, back structure will be CFRP, top will be glass, and we will get it done coating over here with any PVD or your plasma. So this is anyway, we are trying to reach nature. That is our target. Okay, thank you.
So let's thank the speaker. And the next speaker we have is, please. I request Dr. Alfonso to kindly present a memento to Dr. Jamin Desai. We have our next speaker, Dr. Samir S. Khirwadkar from IPR, and he is going to talk on high heat flux test facility at IPR. And I request him to kindly deliver the talk.
Thank you very much. So I would like to thank the organizers for giving me this opportunity. I think it's a special opportunity also because I'm talking for the first time probably in front of the space scientists. I have been talking these things in front of plasma physicists a lot, but not so far in the space region. So in short, I will say let us come back from space in plasma in space to plasma on the Earth. I'll be speaking about the heat management, heat transfer related things, which is generally of interest to everybody. What is happening?
So I know that I am standing between you people and the dinner. I will be short, quick, and will try to escape the questions. So what should we do? Sorry for this delay. I think the PPT was not working. Is this PDF version or PPT? I see. So this point, this is not working. Okay. You can put that clock there for me. Okay, I'll be very quick on this. I already consumed too much of time.
This is about the height first test facility at our institute. Outline of my talk will be, I'll be firstly introducing to you about why this facility was needed, and then actually about the facility, some of the major subsystems, some glimpses, and some future developmental work. So when India became a partner in ITER project in 2006, where the ITER tokamak needs to be built in France, and it has a lot many components. And here you can see the diverter, and first of all, these are the heat plasma facing components, where the core plasma will have a lot of heat which will be coming onto these components, especially the diverter, where we talk about quasi steady state of 10 megawatts per square meter. Then the slow transients of few seconds of 20 megawatts, and then a gigawatt per square meter fast transients of about a millisecond. So these are the components where there are tungsten monoblocks, which are nothing but the tungsten tiles with the coolant flowing through them through a copper pipe. So they are layered here in the form of a chain. They are here, and this is called dome, where it's called macro brush. So I just want to introduce to you this technology which I'll be using, monoblock and macro brush, mostly the monoblock. So because of this kind of a structure, they can handle a lot of thermal stress. So these kind of components are typically, they are expected to work for the steady state heat transfer about 10 megawatts per square meter, and minor variations to about 20 megawatts per square meter. Okay, this is just to give a comparison that typical re-entry vehicles or the heat transfer elements in the reactor, nuclear reactors, few megawatts per square meter, whereas here is the ITER diverter, which will be 10 to 20 megawatts per square meter. We have rocket exhaust 85, and then these are the transient events in the tokamak. That will be few gigawatt per square meter, but small. Here is the information about the ITER-like tokamaks, where the diverters are over here, 5 to 20 megawatts per square meter, 450 seconds, and number of cycles that we study is 10,000. Where the ELMs are 0.5 millisecond and about 10 to the power 6. These are disruptions, and BD is huge energy loss to the components, where there are irreversible degradation of materials. So in order to test these components for the heat transfer, electron beam is generally considered as a good source. I want to just somehow define why it is so. So electron beams are most popular, and there are few facilities in the world. I'll be listing them in the next slides, where they are using electron beams. So firstly, because electric and magnetic fields, you can just use them to change the beam parameters, deflection, power, anything you want, good feedback control also. Electron beams also have a mature technology that allows great reproducibility, because its components here is typical. You have a steady state, like a quasi steady state heat flux. On top of that, you have these transient heat fluxes. And in order to have a very nice repeatability of these heat fluxes, you need to have a very robust, well-proven system and a well-behaved system. So that's why they are good. Also, it is the electrons which are interacting with the material. We are talking about tungsten or metallic materials, and they're chemically inert. So you don't have to bother about other processes like scattering, sputtering, and physical damage with chemical interactions also. Because apart from electron beams, there are ion beams or neutral beams also used to do these studies. And electron beams having low energy are preferred because of the surface heat loss. Typically, in the tokamaks, we talk about few keVs of energies, which will go maybe deeper into few microns into the material. You would like to simulate that kind of a surface heat loads, and that's why here you have energy versus the penetration depth. And for electrons, of course, it is high compared to the other atoms or ions. But still, it is like for 100 keV, it will be like 50 microns for tungsten materials. And we typically, in our facility, we use 50 keV, so about 25 microns. Okay, a quick look at these are the few facilities existing in the world today, and this is our facility, height flux test facility. We have 200 kilowatt beam and 45 kilo electron volt its energy, and this is beam diameter changes with the beam power. As we go to higher power, the diameter increases. So that's why at a lower power we are having more power density like that. So you can see that all these facilities, apart from a few of this RDTF in Russia, and this one is in the US, they're 1200 and 800 kilowatts, whereas rest are about 200 to 400 kilowatts systems. So about high trust test facility at IPR, we established in 2013. That was in a very much a primitive kind of thing at that time. Slowly we evolved and we improved on it. And here, since it is a 200 kilowatt beam, just a simple calculation, if you put this 200 kilowatt onto whatever area in centimeter square on the x-axis versus the heat flux, incident heat flux onto the y-axis, then you can see that you can go from whatever very high numbers, more than 200. I mean, we go up to, if we have a static beam, up to a gigawatt per square meter, down to very low numbers and covering a large area. Depends on how much area you would like to cover. One more good thing about the electron beam, sir, you can position them nicely, deflect them, position them onto, because you may have a big component, but your power of the beam does not allow you to go very high heat plus on a very large area. So you can selectively take a small element of your big component, focus beam on them and test it. Okay, so it is basically designed, this facility is designed to perform heat load experiments for water-cooled plasma fusing components under vacuum environment. Here, mainly the thermal cyclic testing of components under intense quasi-steady state heat flux of the order of 10 megawatts square meter. And typical thermal cycle of each of these heat flux studies is about 30 seconds on and off for the kind of components monoblock I was talking about. However, it will be the period of a cycle will depend on the thermal equilibration time, because once it goes to thermal equilibrium, there is nothing much to disturb your thing. So you have to just take it down, the power take it down, and once again have the next cycle. And then it is also for the thermal cyclic testing of plasma fusing materials, because these in the tokamaks, the materials have, as I said, the fast transients. 1 millisecond kind of a transient, but a gigawatt per square meter, which means you can imagine the kind of damage it is making into the surface of the material with just few microns. So this is the facility. It is having a D-shaped vacuum chamber, and then there is a target handling facility we call here, that on this we place our the jobs, and then this door is closed so that the vacuum chamber is closed. There's electron beam gun on the back side. There is a cryo pump. I'm proud to say that this is developed by Ranjana. He was here. So it is given a gift to us. Whereas there is another cryo pump commercially purchased, and a turbomolecular pump. This is a 5 meter cube kind of a chamber. So the electron beam comes onto the targets, and it can be rastered onto the beam. About a meter by meter kind of a surface area can be easily rastered and have a heat flux. This is how typically the beam is moving around onto the surface. Normally, when you want to cover a surface, you may go in a normal horizontal direction, vertical direction, but it is experimentally we observed that this kind of a mesh type of structure gives a much better uniformity of heat flux. So we also do some kind of a simulations of these things to figure it out. And on the bottom, you have the picture of the facility where this is the main, this one. And this is the high pressure loop, because these components need to be water cooled. This is the cooling supply lines to these components. So just a quick look at what are the subsystems here. These are diagnostics, pyrometers, IR cameras, high-speed cameras, then X-ray radiation. About X-ray radiation, I would like to say that these are electrons of about 45 keV energy. I mean, we can adjust the acceleration voltage, but something like 30 to 45 keV. They are hitting tungsten, so you are producing a lot of X-rays. And that's why one has to have a nice shielding. So this is actually a double-walled vacuum chamber, and it can attenuate the X-rays. Otherwise, a huge amount of radiation load is there. By the way, this facility is approved by AERB also for operation. Then this is about the electron beam system. The 200 kilowatt beam scanning frequency is 10 kilohertz. So very fast scanning can be done, and its residence time at a spot is 10 microseconds. You can increase it, but minimum 10 microseconds. So very fast, it can move from one point to another point like that and cover plus minus 25-degree angle. Typically, this distance between the electron beam gun and the surface is 1.5 meters. So a large area it can cover very fast. This is about the vacuum chamber. Maximum size of the component that can be tested is 2 meter by 1.2 meter by 0.8 meter. We are improving this chamber by adding some external extra chamber also. Then there is a data acquisition control system, completely feedback control system. Anything goes wrong anywhere, the system will take care of it. No burns or nothing, no issues. And this is high pressure water circulation system, which uses a very much good controlled water supply to these components, because we are doing heat transfer experiments. The water has to be flown at very high pressures and temperatures and flow rates also. So 60 bar, this system can give 60 bar pressure, 160 degree centigrade temperature, and 300 LPM flow rate, and with an external stability of plus minus 1% in the pressure, plus minus 5% in temperature and flow rate. This because the temperature is that during heat flow experiments, the heat which is dumped onto the system, it has to be thrown to the atmosphere. And so maintaining this temperature is really, one has to have a very good system. So these are just photographs. In case you people are coming to the labs, you will be seeing all these things personally. Okay, we have done lot many experiments with this. I was giving you some glimpses of various things like heat flux uniformity. So we have to measure and then show it there to others who wants to use it. How good is the uniformity? Electron beam profile measurements. Electron beam being all the charged particles going together in the form of a beam, we have to really maintain the pressure inside the system. It should not be a very good vacuum. It should not be very bad vacuum. So we figured out that what is the best conditions. So we have the pumping arrangement as well as the variable conductance gate walls, so that we can adjust the pressure. There is a piezoelectric feeding gas feeding wall also, and we try to maintain the pressure very nicely, which maintains the beam diameter properly. Then X-ray imaging of the electron beam, as I mentioned, electron beams interacting with the targets and having X-rays. What happens is that thermal imaging, thermal cameras, but that thermal image will come only when the electrons are hitting the surface, and that heat is getting dissipated. Whereas X-rays will be produced as soon as electrons are hitting the surface, X-rays will be produced from there. So rather than thermal, we thought X-ray imaging will be better, but we found that it is a real tough job for us. We have been trying our best to have a X-ray camera kind of a thing, where we can actually make out where is the beam, how much area it is. I'll show you some photographs on that also. We generally do critical heat flux kind of an experiments, because any component you design, you should know how much heat flux it can handle, beyond which it will go into a runaway kind of a mode where you will just burn it out. It will not be able to support whatever heat transfer you are thinking about. There are macro brush and monoblock testings for their performance. It is like medium-sized dome that we have made. I'll be showing some of them, not all of them. Okay. There is also some tungsten coatings we do. We play a lot with the tungsten kind of materials for the other areas also. By the way, I'm very glad to tell you that we also received a prototype Faraday screen from the West Comac in France for testing, which we did successfully. So this is how do I play this video? This is a 30-second video. Is there any way you can click onto that? Yes, yes, it is going on. Yes. So this is the electron beam. That is the monoblock. In the pulse mode, how it is This is a particular experiment on tungsten. This is the dome which is being done, and this is the French Faraday screen. This is for our critical heat flux experiment. This is tungsten monoblock. This is some kind of, and this is the actual facilities video. Okay. Then regarding performance tests, this is how the electron beam diameter, as you work from lower power to higher power, 5 mm, roughly 5 mm to 15 mm, that kind of a beam diameter we get. This is about the uniformity of the heat flux for 1 megawatt per square meter and 2.5 megawatts per square meter onto this graphite tile, which is having space. We have made it in such a way that each one is like a pillar, basically. The heat just goes in one direction onto that. So 1D kind of a thing. So this is about the heat flux uniformity. Then this is about our X-ray imaging experiment, where there is a pinhole camera, then there is a X-ray scintillator, and then there is a high-speed camera. So on this kind of a component which we use for the electron beam profile measurement, there is an alternate arrangement of carbon and tungsten tiles, 100 by 100 mm kind of a dimension way. Now on these tiles we have put the this is the infrared image. You can see the electron beam is rastering onto this thing, and we have got this X-ray image at two different distances from the pinhole of the scintillator, and this is how we are getting. But these are preliminary results. So let me tell you, we are trying to upgrade, because whatever was available in our institute we use, but we are interacting with our other collaborators trying to improve on that. This is about this Faraday this thing. These are copper tubes basically, and then on each one of them we had to put different heat fluxes, and that is how we have done. We on this actually these experiments were done for 250 megawatts per square meter for 400 microseconds. So that is how it looks. Optical emission you can see on these things. It is not mentioned here, but it's 250 megawatts per square meter on these tubes. This is how the electron beam, when it is rastering onto this mock-up. So there is a tube, and then there is copper tungsten tiles, and then electron beam is rastering onto that. This is this kind of a test mock-up is situated here. This is a mask, so that electron beam should not go here and there. Although they are well mannered, we can position them properly, but still we take care that we put a mask, copper mask around that. And then these are the kind of repeated. So this experiment on this particular thing was done. We developed this kind of test mock-ups, small ones. Our aim is to develop small possible test mock-ups and see what best we can do with that. And so this is the first cycle, 500 cycle, like a 12. Typically we do experiments for about 1000 cycles. We feel that is sufficient. Normally these kind of components in actual machine, if we had to put, we had to test them for about 10,000 cycles. But that is too much of time and cost. So we restrict the generator to 1000 cycles. Here is the ultrasonic image from the inside of this tube. The ultrasonic inspection of the copper to tungsten interface before the first cycle and after 1200 cycle, and there is no damage. By the way, here I have not mentioned to you, but heat flux is extracted heat flux is 10 megawatts per square meter. It's somewhere here. Okay, so that was about a quasi steady state kind of a heat flux. Here I'm giving an example of a pulsed or fast transient kind of heat flux. These two materials we developed. This is direct centered pressing pure tungsten and direct center pressing tungsten for 1% lanthanum oxide. So, and there is a commercially from Plancy make commercially grade pure tungsten. They are arranged in a 120-degree sector in a 25 millimeter diameter sample, and then the beam was centered here. So beam is having its own diameter. That means simultaneously on these three sectors we are putting heat load because it's a Gaussian profile. So from that. And there are like this is for about 100 cycles. Each cycle is about 20 millisecond on and off for one second. So each of the cycle is shown here. And after 1,000 cycles, when we look at these two materials which we developed, and then we find that this has shown no problems, whereas here in this particular one, it has shown some cracks of about 15 microns. Our future work, we are going to improve on our X-ray imaging capabilities using some flat panel detectors. Then our facility is capable of handling the ITER like many very big scale components. So in order to view various parts of the components, we are going to install some mirrors, infrared mirrors. So that kind of arrangement has to be done. And then pyrometers, apart from IR cameras, we use pyrometers, but normally pyrometer will focus only at one point, whereas we would like to have automated programming in the sense that we can define the location and pyrometer will be just going on to those locations so as to give the data, and then we can correlate that with the IR images. So from that perspective. Okay, this is another development we are doing is that so far the system was developed looking at the ITER present requirements of water-cooled plasma phasing components. But here we are now going ahead with helium-cooled components because high pressure, high temperature helium gas is also used for these components for heat transfer. And so this system we are going to okay, so we are extending this system. This is existing part. This will be taken away, target handling system, and then it will be having an additional chamber over here, extension chamber, and then one more additional system which is right now being fabricated in Bangalore, and that will be used to supply high pressure, high temperature helium gas to the system. There is something called test blanket modules, if you know, which actually is used for converting neutron energy into the tritium and all using lithium blankets. So for that, we have to. We are also working on the helium-cooled diverters. So you have seen water-cooled earlier, but then these are helium-cooled. So helium gas will be flown, and then so they are small ones like this, is about 32 millimeters. So small, we call them finger-type modules. So we have fabricated one, and we are going to fabricate few more so as to make a small mock-up. And then that will be again tested once this high pressure helium facility is in working condition. This is another one which is actually part of the test blanket model. It is a smaller version of that, and this is already available with us. Only thing is once our facility is ready, we can test it. Okay, as I'm in this plasma for space and aerospace, I thought I should just collect some in slides about some information about what are the other heat loads where this re-entry, and I think you people know very well about these things. This is I think the cone, and this is the silica fibers. This is environmental barrier coatings and the thermal straps. So these are some of the other heat load related applications. So to summarize, height plus facility is established at IPR for height plus testing of plasma components. It is one of the few such test facilities in the world. This 200 kilowatt 45 kV electron beam is used as heat source. And then it is capable of testing components up to 1 ton of weight. And then high pressure water circulation system is capable of providing stable water flow up to 60 bar, 160 degree, 300 LPM. We are improving in the diagnostics, especially on the X-ray imaging. Then new target handling facility to enhance capability of testing helium gas cooled plasma phasing components, and it will be integrated with our helium loop, which is in the adjoining area near to our system. It is coming up already. It will be integrated with that to get the helium high temperature and pressure. So I think that's all. I would like to just finally acknowledge all my colleagues from the division, as well as who have been interacting with so many people, ITER in IO, ITER India, Domestic Agency, BARC, IGCAR, Fluid Control Research Institute, and Nuclear Fuel Complex. Thank you very much.
Now we can take 2 quick questions.
No. It is, as I said, high temperature, high pressure. We are not using right now, but we are establishing that. That is, temperature will be something like 300 to 500 degrees centigrade, and pressure will be 80 bar. So that kind of a pressure and temperature is required. See, we are working with tungsten where it's a ductile to brittle transition temperature is something like 500 degrees, 450, 500 degrees. We need to. No, water cooling is I mean, that is the, I mean, historically, that is the way the water is used for cooling purpose, and that is being used everywhere. From the fusion reactors point of view, in case of water leakages into the tokamak, it can create havoc. Those water will become vapor, and then it can be interacting with the tungsten or even other materials. So that's not good. Whereas if you use helium cooling like that, then even if helium is leaking, it is not an issue for tokamak. So that is this is a futuristic technology. Let me tell you. Sorry. Yes. No, we're not spraying. It is used like a fluid. In the helium gas is flown through the well-defined channels into those structures which I showed. Here, there is a very complex structure of this helium gas which is being flown over here, like that. Exactly. That's it. For heat transfer.
So now let's thank the speaker once again.
I hope I could I mean finish it in reasonable time.
And I request Dr. Alfonso Joseph to kindly present a memento to Dr. Samir. So with this, the second technical session has ended, and we conclude the first day of seminar on plasma for space and aerospace applications, and we look forward to meet you all tomorrow. And now I request everyone to proceed for the departure from FCIPT to IPR for the dinner. And
regarding the transport, like people who come from SAC guest house and SAC thing, the bus is there. Okay, like so that will take you to the IPR guest house for dinner, and then drop you back in the guest house where you alight the bus from morning. And there are a couple of some people who come by traveler, tempo traveler. They also can board the bus. Okay, and after dinner they also will be drop back in the respective hotels. We'll make separate arrangement for that. Okay, so and tomorrow's morning, the same like today, like the SAC guest house, the bus will be waiting at the outside the SAC campus, and you can same time you can preferably 8:30 because